Out there in the abyss exist cosmic powerhouses that are not only rare but also incredibly violent, capable of releasing more energy in a fraction of a second than the Sun produces in 100,000 years. Called Magnetars, these neutron stars possess magnetic fields so intense they could strip the information off your credit card from halfway across the moon. This ferocity makes Magnetars some of the most fascinating objects in space. Let's uncover how these stellar remnants shake the universe with starquakes, influence entire regions of space, and might even hold the key to solving some of astronomy's greatest mysteries. The birth of neutron stars, remnants of stellar catastrophes. We first must understand the neutron star. You see, stars are born, live their lives, and eventually meet their end in spectacular ways. Among the most dramatic of these endings is the supernova, a cosmic explosion of unimaginable energy. Massive stars spend millions of years fusing lighter elements, like hydrogen, into heavier ones, like helium, carbon, and eventually iron. Iron is a special case because it cannot release energy through fusion. As a result, once the star's core fills with iron, it can no longer sustain the outward pressure needed to counteract gravity. The core collapses in a fraction of a second, reaching extreme densities. This collapse triggers a rebound effect, sending shockwaves through the star's outer layers and causing the supernova explosion. After the explosion, what remains is the ultra-dense core, the neutron star. Neutron stars are among the densest objects in the universe. Imagine a star much larger than our Sun collapsing into an object only about 20 kilometers across, roughly the size of a small city. Despite their small size, neutron stars can weigh more than twice the mass of the Sun. This means their density is staggering. A sugar cube-sized portion of a neutron star would weigh as much as a mountain on Earth. This unimaginable density arises from the collapse of the core, which compresses matter to the point where atoms themselves are dismantled. Electrons and protons combine to form neutrons, resulting in an object composed almost entirely of these subatomic particles. Neutron stars spin rapidly, often completing a full rotation in just a fraction of a second. This rotation, combined with powerful magnetic fields, can create fascinating phenomena. Not all neutron stars are the same. Scientists categorize them based on their behavior and characteristics. Pulsars are one type. These neutron stars emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like the light from a lighthouse. If Earth lies in the path of these beams, we detect them as pulses of radiation, hence the name pulsars. Some pulsars rotate hundreds of times per second. These are called millisecond pulsars, and their extraordinary speed is often the result of matter from a nearby companion star being pulled onto their surface, spinning them up over time. Another kind of neutron star is the magnetar. These are even rarer than pulsars and are defined by their incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields can twist and stress the star's crust, leading to violent outbursts called starquakes. When this happens, a magnetar can release as much energy in a single second as the Sun produces in 100,000 years. These bursts of energy can disrupt satellites and communications on Earth if a magnetar is relatively nearby, although such an event is rare. Some have speculated about the existence of an even more exotic type of remnant, the quark star. These hypothetical objects could form if the density of a collapsing star becomes so extreme that neutrons themselves break down into their constituent particles, quarks. If quark stars exist, they would represent a state of matter even more bizarre than that of neutron stars. However, their existence remains unconfirmed, and they are a subject of active research and debate in the scientific community. The two confirmed categories of neutron stars, pulsars and magnetars, are not always distinct. A neutron star can exhibit characteristics of more than one type during its lifetime. For example, a magnetar may also act as a pulsar if its magnetic field aligns in such a way that it emits detectable beams of radiation. What makes a magnetar? Magnetars stand out because of their magnetic fields, which are the strongest known in the universe. These fields are billions of times stronger than those of ordinary neutron stars, and trillions of times stronger than the magnetic field of Earth. When a star collapses into a neutron star, its magnetic field doesn't disappear, it becomes concentrated. Imagine a spinning ice skater pulling their arms in, spinning faster and faster. Similarly, as the star's core shrinks during the collapse, its magnetic field intensifies. For most neutron stars, this results in a magnetic field that is already incredibly strong, thousands or even millions of times more powerful than any field generated on Earth. But for magnetars, the magnetic field reaches another level entirely. The difference lies in how the star evolves during and after its collapse. Scientists have proposed several theories to explain why some neutron stars become magnetars. One idea focuses on the star's rotation. When a massive star is spinning rapidly as its core collapses, the fast rotation can amplify the magnetic field. This process is known as a dynamo effect. If conditions are just right, the collapsing core's magnetic field can grow to an extraordinary strength, giving rise to a magnetar. Another factor may be the star's mass. Theories suggest that stars slightly more massive than those forming regular neutron stars could create the conditions for a magnetar. This is because their higher mass may lead to greater turbulence during the collapse, which could also amplify the magnetic field. However, this isn't the whole story, as not all stars of the same mass produce magnetars. A particularly intriguing theory is that magnetic fields in magnetars may be linked to the structure of the star itself. Inside a neutron star, the matter is packed to incredible densities, creating extreme pressures and temperatures. This environment may allow currents of particles to flow in ways that sustain or even increase the magnetic field. These internal processes, combined with the intense gravitational forces at play, create a setting where magnetism can reach unimaginable levels. Magnetars are not only defined by their magnetic fields, but also by what those fields do. The intense magnetic forces can twist and strain the outer layers of the magnetar, creating stress in the star's crust. Occasionally, this stress becomes too much, leading to sudden and violent shifts called starquakes. These quakes release enormous bursts of energy, sometimes in the form of high-energy X-rays or gamma rays. These bursts can be detected from Earth as powerful flares. The life of a magnetar is thought to be relatively short, at least compared to the lifespan of other neutron stars. As time passes, magnetars slow down. The magnetic field exerts a braking force on the star's rotation. This process, called magnetic braking, occurs as the magnetic field interacts with charged particles in the star's surrounding environment. These interactions produce a stream of particles that carry away angular momentum, reducing the star's spin rate. Magnetars, with their exceptionally strong magnetic fields, experience this braking effect more intensely than other neutron stars. The intense magnetic forces also interact with charged particles around the star, creating electromagnetic waves that carry away energy. This energy loss gradually reduces the magnetar's spin rate. In the early stages, this slowing down might be rapid, with significant changes happening over thousands or tens of thousands of years. Over longer periods, the rotation slows even further, changing the magnetar's behavior. The slowing of rotation has a profound impact on how a magnetar evolves. When a magnetar spins more slowly, it loses much of the rotational energy that initially fueled its emissions. This is one reason older magnetars often become quieter and less active. The bursts and flares seen in younger magnetars are less common as the star ages. However, the strong magnetic fields remain, and these fields can still drive occasional outbursts, especially when stresses build up in the crust of the star. Even though magnetars slow down over time, they remain unique among neutron stars because of their magnetic fields. The fields can last for millions of years, far outliving the initial burst of activity that marks a magnetar's youth. These fields continue to shape the environment around the magnetar, influencing nearby particles and radiation. In some cases, the interaction between the magnetic field and surrounding material can create a faint glow detectable with specialized telescopes. Pulsars versus magnetars, a tale of two stellar beacons. Pulsars are known for their rapid spinning and precise emissions. As a neutron star forms, it inherits the rotation of the collapsing star, and the conservation of angular momentum causes it to spin incredibly fast. Some pulsars rotate hundreds of times per second. These fast rotations, combined with strong magnetic fields, create beams of radiation that shine from their magnetic poles. As the pulsar spins, These beams sweep across the sky like the beam of a lighthouse. If Earth lies in the path of these beams, we detect them as regular pulses of radio waves, X-rays, or gamma rays. The stability of these pulses makes pulsars some of the most precise cosmic clocks ever discovered. Magnetars also spin, but they tend to rotate more slowly than pulsars. A typical magnetar completes one rotation every few seconds, which is much slower than the millisecond speed seen in the fastest pulsars. This slower spin is thought to be due to the intense magnetic fields of magnetars. These fields create powerful forces that can act as a kind of brake, slowing the star's rotation over time. While pulsars shine steadily in the radio spectrum, magnetars are often quieter. Many magnetars emit little or no radio waves at all. This difference is tied to how each star releases energy. Pulsars rely on their rotational energy to power their emissions. As they spin, charged particles are accelerated along the magnetic field lines, generating the radiation we detect. This steady loss of rotational energy slows the pulsar gradually over time. Magnetars, on the other hand, are powered by their magnetic fields rather than their rotation. Their immense magnetic energy dominates their behavior, creating bursts of X-rays and gamma rays rather than steady radio waves. These bursts occur when the stresses in the magnetar's crust become too great, leading to sudden releases of energy. The result is a violent outburst that can briefly make the magnetar one of the brightest objects in the sky. These outbursts are not predictable, making magnetars far less consistent in their emissions compared to pulsars. Pulsars often have active surroundings, with winds of particles and radiation creating nebulae that glow brightly. These pulsar wind nebulae are fueled by the steady energy output of the spinning pulsar. Magnetars are usually more isolated. Their bursts can affect their surroundings, but they do not create the same kind of persistent activity seen around pulsars. Despite these differences, there is some overlap between the two. A few neutron stars exhibit traits of both, blurring the line between the two categories. For example, some magnetars show faint pulsar-like emissions in the radio spectrum, though these are much weaker than those of true pulsars. Similarly, some pulsars can have relatively strong magnetic fields, though not on the scale of magnetars. Magnetic fields in space. Why some stars go extreme. Magnetic fields originate from the motion of charged particles. On Earth, the planet's magnetic field is created by the movement of molten iron in its liquid outer core. This process, known as the geodynamo, is a pretty classic example of how magnetic fields are generated and maintained. The principle is simple. When an electrically conductive material moves within a rotating system, it generates currents that produce a magnetic field. In stars, a similar process occurs on a much larger and more powerful scale. The plasma, or hot ionized gas, that makes up a star's interior moves and rotates, setting up currents that generate and sustain magnetic fields. When a star forms from a collapsing cloud of gas and dust, magnetic fields are already present, although they are relatively weak. As the material collapses under gravity to form the star, the magnetic field lines are pulled inward and compressed. This increases the field's strength, a process similar to squeezing a spring. The rapid rotation of the forming star further influences the magnetic field, twisting and stretching the field lines into more complex structures. The resulting magnetic field is much stronger than it was in the original gas cloud. Most stars maintain relatively stable magnetic fields throughout their lifetimes, with strengths that depend on factors like their size, temperature, and rotation rate. Stars like the Sun have magnetic fields that are constantly changing due to convection currents within their outer layers. These currents, driven by the movement of hot plasma, create loops of magnetic energy that can lead to solar flares and sunspots. In young, rapidly rotating stars, the magnetic fields can be much stronger, leading to even more dramatic flares and eruptions. When a massive star collapses into a neutron star, the star's magnetic field lines are forced into a much smaller volume, dramatically increasing their strength. This process is known as flux conservation. Imagine a rubber band being stretched tightly around a shrinking object. The tension in the band increases as the object gets smaller. Similarly, the magnetic field becomes far more intense as the star's core contracts. For most neutron stars, the resulting magnetic fields are already extremely strong. But in rare cases, the combination of rapid rotation and specific conditions during the collapse amplifies the magnetic field even further, producing magnetars. The core's rapid spin creates a swirling motion in the plasma. This motion generates electric currents, which in turn produce a magnetic field. If the core is spinning fast enough, these currents can reinforce the magnetic field, causing it to grow exponentially. The turbulence in the core, driven by intense heat and pressure, adds to this amplification, stretching and twisting the magnetic field lines. This process can amplify the magnetic field to the extraordinary levels seen in magnetars. Rapid rotation also causes the core to flatten slightly at its poles, creating an oblate spheroid shape. This deformation can affect how the magnetic field lines are organized, concentrating them along the rotational axis. In some cases, this alignment might enhance the neutron star's ability to emit radiation along its magnetic poles, a characteristic feature of pulsars, and, to a lesser extent, magnetars. Not every collapsing star produces a magnetar. Scientists believe the initial conditions of the star play a crucial role. Stars that rotate especially quickly before their collapse are more likely to produce the rapid spins needed for a dynamo effect. Similarly, stars with certain mass ranges may have the right internal structures to create the turbulence and flows necessary to sustain the amplification process. The rarity of magnetars suggests that these conditions are relatively uncommon, making these stars an exceptional outcome of stellar evolution. The resulting magnetic fields in magnetars are so strong that they influence every aspect of the star's behavior. They shape the surface, causing stresses that can lead to starquakes and bursts of energy. These fields are so powerful that they even distort the atomic structure of matter, stretching atoms into elongated shapes. This extreme environment is unlike anything else in the universe. Hidden magnetars, discovering the invisible titans. Magnetars seem extraordinarily eye-catching, but not all of them are as easy to find as one might expect. The ones we know about have been detected because of their dramatic behavior, powerful X-ray flares, gamma-ray bursts, and other high-energy emissions that make them stand out in the cosmic landscape. Yet, scientists believe there could be many more magnetars lurking in the universe, hidden from view. These invisible titans might not show the same explosive activity as their more obvious counterparts, making them far harder to detect. Still, their existence can be inferred through certain indirect clues. One reason some magnetars might remain hidden is that their activity diminishes over time. Magnetars are most active when they are young, releasing bursts of energy driven by their immense magnetic fields. As they age, they lose rotational energy, and their magnetic fields weaken. Without the dramatic emissions associated with these forces, an older magnetar might appear quiet, blending in with the vast sea of other neutron stars. These dormant magnetars, though inactive, still retain their incredibly dense structure and strong, though decaying, magnetic fields. The absence of observable X-rays or gamma rays also doesn't mean these magnetars have vanished. One clue comes from their gravitational influence. Magnetars, like all neutron stars, have incredibly strong gravitational fields due to their immense mass packed into a tiny volume. This gravity can affect nearby objects, such as companion stars in binary systems. If a star's orbit shows irregularities that can't be explained by a visible companion, it could be the result of a hidden neutron star, possibly a dormant magnetar. Another clue might come from the influence of magnetic fields on surrounding space. Even if a magnetar no longer emits bursts of energy, its magnetic field can still interact with particles and radiation in its vicinity. This interaction might create faint, low-energy signals, detectable by highly sensitive instruments. For example, charged particles spiraling along magnetic field lines could emit faint radio waves. These signals are far weaker than the bursts seen from active magnetars, but could still provide a signature of their presence. Astronomers are also exploring the possibility of finding hidden magnetars through their effects on pulsar timing. Pulsars emit regular pulses of radio waves as they spin. If a magnetar is nearby, its gravitational or magnetic field could subtly distort these signals. This would appear as tiny irregularities in the timing of the pulses, offering an indirect way to detect hidden magnetar. The search for hidden magnetars is challenging, but advances in technology are opening new possibilities. Instruments like the Square Kilometre Array, an upcoming radio telescope, will be capable of detecting extremely faint signals from across the universe. By scanning the skies with unprecedented sensitivity, astronomers will hopefully uncover the subtle signatures of dormant magnetars, identifying them even in the absence of dramatic bursts. Some scientists have speculated that hidden magnetars might also be responsible for unexplained phenomena in other areas of astrophysics. For instance, the strong magnetic fields of a dormant magnetar could distort the signals from distant objects, creating anomalies in the data that don't match known patterns. Investigating these anomalies could lead to the discovery of magnetars that have eluded detection. The number of known magnetars is relatively small, with only about 30 confirmed examples in our galaxy. However, based on the number of massive stars that have gone supernova over the history of the Milky Way, there could be hundreds or even thousands of magnetars, most of them hidden. If this is true, then our understanding of the population of neutron stars and the role magnetars play in the galaxy might need to be significantly revised. Magnetars in binary systems, a rare cosmic dance. Magnetars are rare by themselves, but finding one in a binary star system is an even more exceptional occurrence. Binary systems, where two stars orbit a common center of gravity, are not uncommon in the universe. In fact, a significant percentage of stars are part of such systems. However, the discovery of a magnetar paired with a companion star presents a unique opportunity to study how these incredibly dense and magnetically powerful objects interact with their stellar neighbors. When a massive star ends its life in a supernova explosion and collapses into a neutron star, the binary system it was part of can survive, depending on how much mass and energy are ejected during the explosion. If the gravitational bond between the two stars remains intact, the newly formed neutron star continues to orbit alongside its companion. In rare cases, if the resulting neutron star is a magnetar, the intense magnetism and radiation it emits can have profound effects on its partner. The magnetic field of a magnetar is so strong that it extends far beyond the star itself, influencing the surrounding space. Any charged particles in the magnetar's vicinity, including those from the companion star's stellar wind, can be caught and accelerated along the magnetic field lines. This interaction creates streams of high-energy particles that can bombard the companion star, potentially stripping away its outer layers. Over time, this process can erode the star's atmosphere, altering its structure and evolution. Magnetars are known for their bursts of X-rays and gamma rays, which are some of the most energetic forms of radiation in the universe. These bursts can heat the surface of the companion star, causing localized eruptions of material or even long-term changes in the star's behavior. In some cases, the intense radiation can lead to the formation of a bow shock, where the stellar wind from the companion star collides with the magnetar's radiation, creating a turbulent boundary between the two. In systems where the stars are very close together, the magnetar's gravitational pull can draw material away from its companion, forming an accretion disk around the magnetar. As this material spirals inward, it releases energy in the form of heat and radiation, creating a highly luminous system. The accretion process can also affect the magnetar's rotation, slowing it down or altering the alignment of its magnetic field. Over time, the exchange of mass and energy between the two objects can cause their orbits to shrink or become more elliptical. In extreme cases, the stars can spiral closer together until they merge, producing an explosive event that could create a black hole or another high-energy phenomenon. Such mergers are rare, but are thought to be responsible for some of the brightest and most energetic events observed in the universe. Observing these systems allows astronomers to study how extreme magnetic fields interact with matter and how these interactions influence the evolution of stars. These systems also serve as natural laboratories for testing theories about the behavior of neutron stars and the forces that govern their environments. One intriguing aspect of magnetars in binary systems is their potential role in producing gravitational waves. When two massive objects in a binary system interact, their movements can create ripples in spacetime that propagate outward as gravitational waves. If the magnetar and its companion star have a close and dynamic relationship, their gravitational interactions could produce detectable waves. Observing such waves would provide a new way to study these systems, revealing details about their masses, orbits, and internal structures. Despite their scientific importance, magnetars in binary systems are extremely rare, with only a few confirmed examples. This rarity is partly due to the difficulty of forming such systems. The conditions required to create a magnetar, a massive, rapidly rotating star that undergoes a highly energetic collapse, are already uncommon. Adding a companion star that survives the supernova explosion and remains gravitationally bound to the magnetar further narrows the possibilities. As a result, these systems are among the most unusual in the cosmos. This rarity also makes them challenging to study. The powerful emissions from the magnetar can overshadow the signals from the companion star, making it difficult to observe the system as a whole. Additionally, the interactions between the two stars are often so complex that interpreting the data requires advanced models and simulations. Magnetars and the neutron star equation of state. Neutron stars exist at the boundary of matter's physical limits, where atomic nuclei are compressed to densities so extreme that a single teaspoon of neutron star material weighs billions of tons. This staggering density has driven scientists to develop the neutron star equation of state. The equation of state describes how matter behaves under these extraordinary pressures and densities, offering a framework to understand the inner workings of neutron stars. Magnetars, with their immense magnetic fields, introduce additional complexities, potentially stretching current models and revealing unknown aspects of particle physics. The equation of state for neutron stars is essentially a relationship between pressure, density, and temperature inside the star. It is a critical tool for predicting how a neutron star forms, evolves, and interacts with its environment. The matter inside these stars is not like anything we encounter on Earth. Under extreme pressures, electrons are forced to combine with protons, creating neutrons. These neutrons, packed into an almost solid form, dominate the structure of the star. The exact properties of this dense matter remain one of the biggest mysteries in astrophysics, because they cannot be recreated in laboratories. Then come magnetars. Their magnetic fields are so strong that they influence the behavior of particles at a fundamental level. Fields of this magnitude can distort the shape of atoms and even alter the structure of the neutrons themselves. As a result, the equation of state for a magnetar might differ significantly from that of a typical neutron star. The immense magnetic pressure could counteract some of the gravitational compression, slightly altering the star's size and shape. These effects need to be factored into any accurate model of neutron star physics. In a magnetar, particles experience forces that are not only gravitational, but also magnetic. These forces can change the energy levels of particles, affecting how they interact with each other. For example, the magnetic field could create regions where particles align in specific ways, forming structures that wouldn't exist in less extreme conditions. These effects are subtle but crucial for understanding the full picture of a magnetar's interior. Magnetars also provide a unique environment to study quantum electrodynamics, the theory describing how light and matter interact at the quantum level. In the presence of such strong magnetic fields, even the vacuum of space behaves differently. Normally, empty space is thought to be inert, but in a magnetar's magnetic field, it can become polarized, affecting the way light travels through it. This phenomenon, known as vacuum birefringence, offers a rare opportunity to test theories of fundamental physics in conditions that cannot be reproduced on Earth. At the extreme densities found in neutron stars, some theories predict that neutrons might break down into their constituent quarks, creating a form of matter known as quark-gluon plasma. If magnetars reach these densities, their intense magnetic fields could influence how this transition occurs, potentially stabilizing certain configurations of quarks. Observing such effects would provide invaluable insights into the behavior of matter at its most fundamental level. In the core of a neutron star, neutrons are thought to form a superfluid, a phase of matter where particles move without friction. Similarly, protons might form a superconducting state where electric currents flow without resistance. Magnetars, with their powerful magnetic fields, could disrupt these states, altering the flow of matter and energy, within the star. By studying how magnetars emit X-rays, gamma rays, and other forms of radiation, scientists can infer details about their structure and behavior. For instance, the frequency and intensity of a magnetar's bursts can provide clues about the stresses within its crust. These stresses, caused by the magnetic field, offer a window into the star's internal properties, helping refine the equation of state. Instruments like the Neutron Star Interior Composition Explorer, or NISA, installed on the International Space Station, are designed to measure the properties of neutron stars with unprecedented precision. By analyzing the light from magnetars, NISA can provide data on their size, mass, and other properties, helping to constrain models of their interiors. Theoretical research is also pushing the boundaries of what we know about magnetars. Simulations using powerful supercomputers are allowing scientists to model the effects of extreme magnetic fields on matter. These models are helping to predict how magnetars evolve over time and how their properties might differ from those of other neutron stars. The magnetic evolution, why magnetars don't stay the same. Like the stars they once were, magnetars are dynamic and ever-changing. Their magnetic fields evolve significantly over time. This evolution can transform an active and volatile magnetar into a quieter, less conspicuous stellar remnant. Magnetic fields in magnetars are not immune to decay. Over time, the processes driving these fields diminish their strength. This decay happens for several reasons. One major factor is the movement of electric currents within the magnetar. Magnetic fields are generated by these currents, which flow through the star's dense interior. However, as time passes, these currents lose energy and dissipate, causing the magnetic field to weaken. Another contributor is the crust of the magnetar. The crust is not a simple solid shell, but a lattice of atomic nuclei, compressed to extraordinary densities. The immense stresses created by the magnetar's magnetic field can cause starquakes, allowing the magnetic field to rearrange itself. Over time, the rearrangement can lead to a reduction in the field's intensity or a change in its structure. The energy stored in a magnetar's magnetic field is not infinite. Each powerful flare or burst of radiation emitted by a magnetar draws on this reservoir of energy. As the magnetar ages and releases more bursts, the energy in its magnetic field is gradually depleted. Eventually, the magnetic field can no longer sustain the dramatic activity that defines an active magnetar. At this point, the magnetar becomes quieter, behaving more like a typical neutron star. The timescale of magnetic decay in magnetars is thought to be relatively short in cosmic terms, on the order of tens of thousands to a few 100,000 years. This is much shorter than the lifespans of many other celestial objects, which often span millions or billions of years. This rapid evolution explains why only a small number of magnetars are currently active and detectable. Many others have likely already transitioned into quieter states. Despite this decay, traces of the original magnetic field often remain. Even in a weakened state, the field can influence the star's environment, albeit on a smaller scale. For instance, the residual magnetic field may still affect the motion of charged particles around the neutron star, creating faint emissions that could reveal the star's past as a magnetar. The evolution of a magnetar's magnetic field is also not a uniform process, and different regions of the star may experience decay at different rates, leading to a complex and uneven weakening of the field. This non-uniformity can create localized regions of high magnetic intensity, even as the overall field declines. These regions might occasionally produce smaller flares or bursts. Although rare, some magnetars may experience periods of relative quiet, only to reactivate later. This reactivation could occur if stresses within the star's crust build up to a critical point, causing a sudden rearrangement of the magnetic field. Birth in chaos. Magnetars, emerging from supernovae. For a magnetar to emerge, specific and extraordinary factors must align. The mass of the progenitor star, its rotation rate, and the dynamics of its collapsing core all play crucial roles in determining whether a magnetar is formed. The journey to becoming a magnetar begins long before the supernova itself. A massive star, one with a mass at least 8 times that of the Sun, spends millions of years fusing lighter elements into heavier ones in its core. This process provides the energy needed to counteract the force of gravity, keeping the star stable. Over time, however, the core accumulates iron, an element that cannot undergo fusion to produce energy. When the iron core reaches a critical mass, it succumbs to gravity and collapses under its own weight. During this collapse, the core is compressed to extreme densities. This process happens incredibly quickly, in just fractions of a second. The collapsing core halts abruptly when the neutrons form a solid-like structure, rebounding outward and generating a powerful shockwave. This shockwave tears through the outer layers of the star, causing the supernova explosion. For a magnetar to emerge from this chaos, the progenitor star must possess certain characteristics. One key factor is the mass of the star. Stars that are too massive tend to collapse directly into black holes, bypassing the neutron star stage altogether. On the other hand, stars that are too small may not produce the extreme conditions needed to create a magnetar. Stars in the right mass range, typically between 10 and 25 times the mass of the Sun, strike the right balance. Before the supernova, the progenitor star must also be spinning rapidly. This rapid rotation amplifies the magnetic field through the dynamo mechanism. This increase in rotation rate generates enormous amounts of energy, which can be channeled into strengthening the magnetic field. Some theories suggest that the initial rotation rate must fall within a narrow range. If the core spins too slowly, it may not generate a strong enough magnetic field to form a magnetar. Conversely, if it spins too quickly, the dynamics of the collapse might favor the formation of a black hole instead of a neutron star. The magnetic field itself originates from the motion of charged particles within the collapsing core. During the collapse, the intense compression of matter and rapid rotation create conditions for a magnetic dynamo to operate on an unprecedented scale. This dynamo amplifies any pre-existing magnetic field to extreme levels. The details of this amplification process are not fully understood, but it likely involves interactions between the star's core and its surrounding layers. Another factor influencing magnetar formation is the environment within the collapsing star. The density, temperature, and composition of the core all play roles in shaping the outcome. For example, the presence of heavy elements like oxygen and silicon in the core can affect how the collapse unfolds and how energy is distributed. These factors can influence whether the magnetic field grows strong enough to produce a magnetar or remains weaker, resulting in a typical neutron star or pulsar. Supernovae themselves vary widely in their properties, and this diversity affects the formation of magnetars. Some explosions are more asymmetric than others, with uneven shock waves that may alter the conditions within the core. In some cases, these asymmetries might favor the creation of a magnetar, while in others, they could disrupt the processes needed to amplify the magnetic field. Observations of supernova remnants provide clues about these variations, helping scientists piece together the steps leading to magnetar formation. The quiet magnetars. Not all magnetars maintain their intense activity throughout their lives. Some seem to go quiet, their bursts becoming rare or even non-existent. These quiet magnetars are a puzzling subset of these exotic neutron stars, raising questions about whether they are truly inactive or simply hiding from detection. One possibility is that quiet magnetars are experiencing magnetic decay. Magnetic decay occurs as the intense stresses within the magnetar's crust cause rearrangements in the magnetic field. These rearrangements release energy, but as the field diminishes, the energy output decreases. In younger, active magnetars, these changes are dramatic, often triggering starquakes and bursts of radiation. In older magnetars, the decay becomes less pronounced, and the associated emissions may fall below detectable levels. Magnetic decay is influenced by several factors, including the initial strength of the magnetic field and the composition of the magnetar's crust. The crust plays a critical role in regulating the star's activity, acting as both a reservoir and a barrier for magnetic energy. In some magnetars, the crust may be thicker or more rigid, slowing the decay process and allowing the star to remain active for longer periods. In others, the crust may be less resistant to magnetic stress, leading to a more rapid decline in activity. Magnetars, like other neutron stars, lose rotational energy over time due to the emission of radiation and particles. This process, known as spin-down, is especially rapid in magnetars because of their strong magnetic fields. As the spin rate decreases, the star's ability to generate bursts of energy may diminish. The relationship between spin rate and activity is complex, and not all magnetars follow the same pattern. However, slower rotation generally means less energy is available to power the dramatic outbursts associated with active magnetars. Some magnetars may also become quiet simply because they have exhausted their available energy. During their early stages, magnetars release enormous amounts of energy stored in their magnetic fields. Over time, this energy reservoir depletes, leaving little to drive further activity. These exhausted magnetars may still possess strong magnetic fields, but without a mechanism to tap into their energy, they appear dormant. Quiet magnetars may emit primarily in lower energy wavelengths, such as radio waves or soft X-rays, which are harder to detect. They may also have lower overall luminosity, making them indistinguishable from other types of faint neutron stars. In some cases, quiet magnetars might only be detectable through their gravitational or magnetic influence on nearby objects. One example of a potential quiet magnetar is the neutron star RxJ 1856.5-3754. This star, located about 400 light-years away, is one of the closest neutron stars to Earth. It emits soft X-rays, but lacks the dramatic bursts associated with active magnetars. Some researchers have speculated that RxJ 1856.5-3754 could be an old, quiet magnetar whose activity has waned over time. Another intriguing case is XTEJ 1800-10197, a magnetar that was initially discovered through its bursts of X-rays, but later became detectable in the radio spectrum. This magnetar went through a long period of quiescence, showing little activity before reawakening with new bursts. Such behavior suggests that even apparently quiet magnetars may retain the potential for sporadic outbursts, making them harder to classify. Unlike X-rays and gamma rays, radio waves can travel through regions of space that are opaque to higher energy radiation. This capability allows astronomers to search for magnetars in environments where other signals might be blocked. However, not all magnetars emit detectable radio waves, and the mechanisms behind this variability are not fully understood. Despite their challenges, quiet magnetars remain an important area of research. They may represent a transitional phase in the life cycle of magnetars, offering insights into how these stars evolve over time. They may not necessarily be inactive. Perhaps they may simply operate on different timescales, or emit energy in ways that are harder to detect. Can a pulsar become a magnetar? Unraveling transformations. Though they both might be neutron stars, their defining characteristics, pulsars being steady emitters of periodic radio waves and magnetars being marked by intense magnetic fields and violent bursts, set them apart. One possible pathway for a pulsar to develop a magnetar-like magnetic field involves accretion. In binary systems, where a pulsar has a companion star, the pulsar can pull matter from its partner. This process, known as accretion, is often associated with changes in the neutron star's rotation and magnetic field. As the infalling matter spirals onto the pulsar's surface, it can carry angular momentum, causing the pulsar to spin faster. This spin-up effect, observed in millisecond pulsars, has already been studied extensively. However, the same accretion process might also amplify the pulsar's magnetic field under certain conditions. Dynamos are processes that convert kinetic energy, like rotational energy, into magnetic energy. For a dynamo to operate within a pulsar, the star's interior must have a certain level of fluid motion or turbulence, which can interact with its rotation to amplify the magnetic field. While dynamos are commonly associated with stars during their early formation stages, there is speculation that conditions in a pulsar undergoing accretion could mimic those environments, potentially boosting its magnetic field to magnetar levels. Another way a pulsar might evolve into a magnetar is through binary interactions that extend beyond accretion. In some binary systems, the companion star's death can create a dramatic environment. For example, if the companion undergoes its own supernova or collapses into another compact object, the gravitational and magnetic interactions between the two stars could drastically affect the pulsar. These events might lead to changes in the pulsar's spin and energy balance, possibly influencing its magnetic field. The idea here is that the system as a whole might generate conditions conducive to magnetic amplification. Neutron stars are not static objects. They evolve over time as their interiors cool and their magnetic fields shift. In a pulsar, the initial magnetic field may have a complex structure, with some parts buried beneath the surface or suppressed by the star's crust. Over time, internal movements in the star's superfluid core or the gradual relaxation of stresses in the crust could bring buried magnetic fields to the surface. If the underlying field is strong enough, this process could result in a pulsar acquiring magnetar-like magnetic strength. Observations of some high magnetic field pulsars suggest that this scenario may already occur in nature, though it is not clear whether these objects are intermediate stages or unique cases. One challenge in considering pulsar to magnetar transformations is that for magnetars, the prevailing theory is that their extreme fields originate during their birth. If a pulsar were to become a magnetar, it would require a secondary process to replicate these early dynamo conditions. One possible trigger could be a merger event, such as when a pulsar collides with a white dwarf or another neutron star. The immense energy released in such collisions could create conditions for magnetic field amplification, potentially transforming the pulsar into a magnetar-like object. This idea ties into observations of magnetars in environments associated with dense stellar populations, where such interactions are more likely to occur. There is also the possibility that some pulsars might already be magnetars in disguise. Not all magnetars exhibit the violent outbursts or strong X-ray emissions typically associated with them. Some may appear more like regular pulsars because their activity levels are lower, or their magnetic fields are less evident. In such cases, the distinction between pulsars and magnetars becomes blurred. Observations provide some support for the idea of transitional objects. High magnetic field pulsars, which have magnetic fields stronger than most pulsars but weaker than typical magnetars, occupy an intriguing middle ground. These stars exhibit characteristics of both pulsars and magnetars, such as regular radio emissions alongside sporadic X-ray bursts. They may represent a phase in which a pulsar is evolving toward magnetar-like behavior or a separate class altogether. Magnetic decay and the aging of magnetars. Magnetic decay begins shortly after a magnetar forms. When a massive star collapses into a neutron star, its magnetic field intensifies dramatically due to the conservation of magnetic flux. This compression creates the extreme fields seen in magnetars, but these fields exist in a dynamic, highly stressed state. The crust of the magnetar struggles to contain these immense magnetic forces. Over time, as the stresses build, the magnetic field undergoes rearrangements, releasing energy in the form of high-energy radiation and, in some cases, violent starquakes. The energy released during these rearrangements contributes to the dramatic bursts and flares that characterize active magnetars. However, each rearrangement also depletes the magnetic field slightly, reducing its overall strength. This process is not uniform. It depends on the structure of the magnetic field and the properties of the magnetar's crust. Over thousands to millions of years, these small losses accumulate, gradually diminishing the magnetar's power. One of the key factors influencing magnetic decay is the conductivity of the magnetar's crust. In a highly conductive crust, magnetic fields can persist for longer periods because the electric currents sustaining them are less likely to dissipate. However, magnetar crusts are subject to extreme conditions, including immense pressures and temperatures. These conditions can alter the crust's properties, allowing electric currents to weaken and the magnetic field to decay. Variations in crust composition and structure may explain why some magnetars remain active for longer periods. Magnetic decay is closely tied to the thermal evolution of a magnetar. Newly formed magnetars are extremely hot, with temperatures reaching millions of degrees. This heat affects the conductivity of the crust, facilitating the movement of electric currents and sustaining the magnetic field. As the magnetar cools over time, the crust becomes less conductive, accelerating the decay process. The rearrangement of the field can generate small-scale magnetic loops and knots, which may store energy in localized regions. These structures can release energy sporadically, producing bursts or flares, even in aging magnetars. Magnetars located in dense star-forming regions may interact with surrounding gas and magnetic fields, influencing their own decay processes. Similarly, magnetars in binary systems may experience gravitational or magnetic interactions with their companions, potentially altering their magnetic evolution. Theoretical models suggest that the decay is driven by a combination of processes, including crustal conductivity, core dynamics, and magnetothermal interactions. However, many details are still uncertain, particularly regarding how these processes operate under the extreme conditions inside a magnetar. Explosions at the edge of physics. Could magnetars trigger hypernovas? Magnetars represent some of the most extreme objects in the universe, and their behavior often defies conventional understanding, challenging scientists to think beyond the usual rules of astrophysics. One intriguing question is whether these stellar giants could trigger events even more violent than supernovas, explosions so powerful they are termed hypernovas. Hypernovas are explosions that release up to 100 times the energy of a typical supernova. While supernovas already rank among the most energetic events in the universe, hypernovas stand in a category of their own, often linked to the formation of black holes or gamma-ray bursts. Some researchers speculate that under rare conditions, the unique properties of a magnetar could be the driving force behind such an extraordinary outburst. The birth of a magnetar occurs during the core collapse supernova of a massive star. In this process, the star's core rapidly condenses into an incredibly dense object, while the outer layers are violently expelled into space. For most stars, this results in a neutron star or black hole, accompanied by the brilliant light of a supernova. But in rare cases, if the collapsing core forms a magnetar, its powerful magnetic field could amplify the energy of the explosion, potentially crossing the threshold into hypernova territory. Newly formed magnetars often spin at incredibly high speeds, hundreds or even thousands of rotations per second. This rapid rotation, combined with the star's intense magnetic field, creates a dynamo effect capable of storing vast amounts of energy. If this energy were to be released suddenly, it could drive a hypernova explosion. The key lies in how the magnetar's rotation interacts with its magnetic field over time. Magnetic braking, where the field slows the star's spin by converting rotational energy into electromagnetic radiation, could reach a tipping point. The sudden release of this energy might trigger the kind of outburst that characterizes a hypernova. Magnetars are known for their starquakes and magnetic reconnections, processes that release enormous amounts of energy in localized bursts. In some scenarios, these instabilities could cascade, with smaller magnetic events feeding into larger ones, culminating in a catastrophic failure of the star's structure. If such a collapse occurred while the star was still surrounded by its dense outer layers, the energy released could dramatically exceed that of a standard supernova, producing a hypernova instead. This idea is supported by theoretical models, suggesting that the combination of strong magnetic fields and rapid rotation can amplify the outward energy of a core collapse event. Computer simulations of such scenarios show that magnetar-driven explosions could produce shock waves powerful enough to eject material at speeds approaching a significant fraction of the speed of light. These shock waves would not only account for the extraordinary brightness of hypernovas, but also their association with long gamma-ray bursts, intense beams of radiation emitted during the explosion. Observational evidence for this connection is still scarce, but tantalizing clues exist. Certain gamma-ray bursts have been linked to hypernovas, and in a few cases, researchers have identified remnants of massive explosions with energy outputs consistent with magnetar activity. These remnants often contain unusual patterns of chemical elements, such as elevated levels of nickel, which suggest an explosion far more energetic than a typical supernova. While direct evidence tying magnetars to these events is lacking, the theoretical groundwork is compelling enough to warrant further investigation. One challenge in confirming this hypothesis lies in the rarity of hypernovas. Even among the millions of stars in a galaxy, only the most massive ones are capable of producing such an explosion. The odds of a magnetar forming in these systems and then triggering a hypernova are correspondingly low. This rarity makes it difficult to gather enough observational data to draw firm conclusions. Another line of inquiry involves studying the remnants of hypernovas and comparing them to the signatures left behind by magnetars. For example, researchers could look for the high-energy X-rays and gamma rays characteristic of magnetar activity within the debris fields of hypernovas. Additionally, the presence of unusually strong magnetic fields in these remnants could provide indirect evidence of a magnetar's involvement. If magnetars can indeed trigger hypernovas, this process might play a significant role in shaping the evolution of galaxies. Hypernovas release enormous amounts of energy and material into their surroundings, enriching the interstellar medium with heavy elements like iron, nickel, and gold. These elements are essential for the formation of planets and ultimately, life. In this sense, magnetars and hypernovas could be critical drivers of cosmic evolution, seeding galaxies with the building blocks of complex systems. Magnetars and starquakes, when crusts crack under pressure. Magnetars, with their incredible magnetic fields, are not static objects. Their outer is under constant strain from the forces generated by the intense magnetic field surrounding and permeating the star. These fields can create pressures that exceed the strength of the crust, causing starquakes, releasing vast amounts of energy into space, often in the form of X-rays and gamma rays. Starquakes are among the most energetic processes observed in magnetars, and they reveal a great deal about the internal dynamics of these exotic objects. The crust of a neutron star is composed of highly compressed matter arranged into a lattice of nuclei, surrounded by a sea of electrons. The gravitational forces on a neutron star are so extreme that this crust, despite being just a few kilometers thick, is one of the hardest known materials in the universe. However, even this extraordinary rigidity has its limits when faced with the stresses exerted by a magnetar's magnetic field. Magnetic fields in magnetars can twist and distort the crust, creating tension that builds up over time. When the crust can no longer withstand the stress, it cracks, leading to a sudden and violent release of energy. In some cases, the magnetic field lines threading through the crust can become twisted, either by differential rotation or by shifts in the interior of the star. These distortions act like elastic bands, storing energy as they are stretched. When the magnetic stresses exceed the breaking point of the crust, the field lines snap into a more stable configuration, releasing their stored energy. This process can generate seismic waves within the crust, analogous to earthquakes on Earth, but on a much larger scale. The released energy travels outward, producing electromagnetic radiation that can be detected by telescopes. The initial burst of energy is often followed by a series of smaller emissions, which astronomers call afterglows. These afterglows provide clues about the magnetar's environment and the structure of its magnetic field. The patterns of these emissions suggest that starquakes can significantly reshape the magnetic field of a magnetar, potentially altering its long-term activity and behavior. Starquakes are not uniform events. Their size and impact depend on several factors, including the strength and configuration of the magnetar's magnetic field, the age of the star, and the composition of its crust. Younger magnetars, which typically have more extreme magnetic fields, are more prone to frequent and intense starquakes. Older magnetars, whose fields have decayed over time, may still experience quakes, but these are generally less energetic. Observations of starquakes have provided valuable insights into the physics of magnetars. For example, the study of soft gamma-ray repeaters, a class of highly energetic bursts associated with magnetars, has revealed that these events often coincide with rotational changes in the star. These changes are thought to result from shifts in the star's crust during a quake, which alter its moment of inertia. By measuring these rotational changes, astronomers can estimate the scale of the quake and the forces involved. In some cases, a single quake may set off a chain reaction, destabilizing other parts of the crust or altering the magnetic field in ways that lead to additional bursts. These cascading effects can prolong the activity associated with a quake, creating extended periods of X-ray or gamma-ray emission. Over time, repeated quakes and the associated release of energy may contribute to the decay of a magnetar's magnetic field. As the field weakens, the stresses on the crust decrease, leading to fewer and less intense quakes. This process may mark the transition of a magnetar into a more quiescent neutron star, such as a standard pulsar or a faint X-ray source. The exact mechanisms that trigger quakes and the processes by which energy is converted into electromagnetic radiation are still subjects of active research. Some theories suggest that quakes might involve interactions between the star's crust and its superfluid core, while others emphasize the role of magnetospheric currents in shaping the observed emissions. Starquakes may also have implications for gravitational wave astronomy. The sudden shifts in a magnetar's crust during a quake could produce gravitational waves. While these signals are expected to be weak compared to those from mergers of neutron stars or black holes, their detection would provide a new way to study magnetars and the forces at work within them. Future gravitational wave observatories with greater sensitivity may be able to pick up these signals. Magnetar outbursts versus pulsar glitches. When starquakes cause crust fractures, it disrupts a magnetar's magnetic field, triggering a release of energy that can result in a dramatic outburst. Magnetar outbursts are some of the most energetic events in the cosmos because the magnetic fields in magnetars can exceed a quadrillion Gauss. Magnetar outbursts manifest in several ways. The most common are short bursts, which last less than a second and release energy equivalent to what the Sun emits in days. Occasionally, a magnetar will experience a giant flare, a rare and even more powerful event. These flares release energy in seconds that exceeds the Sun's output over 100,000 years. The bursts are usually accompanied by intense gamma-ray and X-ray emissions, and their sheer brightness can saturate space-based detectors, complicating precise measurements. In contrast, pulsar glitches are not driven by magnetic activity, but by the rotational dynamics of the neutron star. Pulsars, which are rapidly spinning neutron stars, have incredibly stable rotation rates. Over time, however, some pulsars experience sudden increases in their spin rates, known as glitches. These changes are slight, on the order of a few parts per million, but they are significant enough to alter the timing of the pulses, which are usually precise to a fraction of a millisecond. The underlying cause of pulsar glitches is tied to the unique composition of a neutron star. Beneath the crust lies a superfluid interior, where neutrons move without viscosity. This superfluid is decoupled from the solid crust, meaning the two rotate independently. Over time, rotational forces can cause the superfluid to build up angular momentum relative to the crust. When the difference becomes too great, the superfluid transfers angular momentum to the crust in a sudden burst, speeding up the star's rotation and creating a glitch. The observational signatures of pulsar glitches are markedly different from Magnetar outbursts. Instead of emitting bursts of electromagnetic radiation, pulsar glitches are detected through changes in the timing of the star's pulses. Astronomers track these pulses with incredible precision, so even a minute change in spin rate is immediately noticeable. After a glitch, the pulsar's rotation gradually returns to its previous rate, a process called post-glitch relaxation. This recovery provides valuable information about the internal structure and dynamics of the neutron star. Magnetar outbursts and pulsar glitches share some commonalities. Both phenomena involve the release of stored energy. Both are also influenced by the neutron star's crust. Additionally, both events provide unique windows into the extreme physics of neutron stars, offering clues about their structure, composition, and behavior. One key distinction lies in the energy scales involved. Magnetar outbursts are vastly more energetic than pulsar glitches, with the former releasing energy equivalent to the total rotational energy of some pulsars. Another difference is their frequency. Pulsar glitches occur relatively frequently in certain pulsars, especially young ones, which tend to have more dynamic interiors. Magnetar outbursts, on the other hand, are rare and unpredictable. Some magnetars may go years or even decades without an outburst, while others experience clusters of activity. This variability makes magnetar outbursts more challenging to study and predict. Interestingly, there is some overlap between these two phenomena in certain neutron stars. Some pulsars exhibit glitches alongside magnetar-like bursts, blurring the line between the two types. This suggests that the magnetic and rotational processes driving these events are not entirely independent and may interact in complex ways. For example, a pulsar with a strong but not extreme magnetic field might experience both rotational glitches and smaller-scale bursts of magnetic activity. Magnetar outbursts are often detected in the X-ray and gamma-ray spectra, requiring specialized space-based telescopes. Pulsar glitches, in contrast, are observed in the radio spectrum, where ground-based observatories track the precise timing of pulses. Could magnetars be hiding the first evidence of a fifth force? Magnetars are extreme environments where the known laws of physics are pushed to their limits. With magnetic fields 1,000 times stronger than those of ordinary neutron stars and densities that rival the nucleus of an atom, these extraordinary conditions invite questions that extend beyond the standard model of physics, including the tantalizing possibility that magnetars might offer clues about a fifth fundamental force. The standard model of particle physics recognizes 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these governs specific interactions in nature, from the behavior of stars to the structure of atoms. However, physicists have long speculated about the existence of a fifth force, a force that could tie together unexplained phenomena or reveal deeper connections between the forces we already know. Magnetars, with their extreme gravitational and magnetic fields, could provide the conditions necessary to test such ideas. If a fifth force exists, it might manifest where matter and energy are so concentrated that conventional physics begins to break down. The strength of a magnetar's magnetic field is such that it could influence the quantum vacuum, the supposedly empty space filled with virtual particles constantly popping in and out of existence. Some theories of a fifth force predict that it could alter the behavior of these virtual particles, leading to observable effects in the star's emissions. For instance, if a fifth force interacts with photons, it could cause changes in the polarization of the light emitted by a magnetar. This effect would be most pronounced in the X-rays and gamma rays that dominate magnetar emissions. Observatories like NASA's NICA and the European Space Agency's future Athena mission are equipped to study these high-energy signals in detail, potentially uncovering deviations from the predictions of known physics. Another avenue of investigation involves the interaction of a fifth force with gravity. Gravity is by far the weakest of the known forces, but it dominates at the large scales of stars and galaxies. Magnetars, with their intense gravitational fields, could serve as a testbed for modifications to Einstein's general theory of relativity. Some theories propose that a fifth force could act as a kind of dark force, influencing matter in ways that are invisible under ordinary circumstances but become detectable under extreme conditions. For example, if a fifth force slightly altered the structure of spacetime around a magnetar, it could affect the star's rotation or the propagation of gravitational waves from starquakes. Magnetars, with their frequent and energetic starquakes, are ideal candidates for generating gravitational waves. If a fifth force exists and interacts with gravity, it could subtly modify the shape or frequency of these waves. Future detectors designed to observe gravitational waves with unprecedented precision could search for such anomalies in signals originating from magnetars. The interior structure of a magnetar also presents opportunities to explore new physics. At the heart of a magnetar, matter is compressed into a state so dense that its properties are not fully understood. While current models describe the matter as a soup of neutrons, protons, and possibly exotic particles like quarks or hyperons, a fifth force could alter these predictions. It might influence the interactions between particles, changing the star's composition, stability, or magnetic field evolution. Observing how magnetars cool over time through neutrino emissions or thermal X-rays could provide indirect evidence of these effects. If dark matter interacts weakly with ordinary matter, magnetars could serve as cosmic detectors for these interactions. For example, dark matter particles might accumulate within a magnetar's core, where the extreme density could enhance their effects. If a novel force mediated interactions between dark matter and ordinary matter, it might lead to observable changes in the star's temperature, rotation, or magnetic activity. The challenge in identifying a fifth force lies in distinguishing its effects from those of known physics. Magnetars are already among the most complex and poorly understood objects in the universe, and their behavior is influenced by a multitude of factors. Separating subtle deviations caused by a fifth force from the noise of magnetic reconnection, particle interactions, and rotational dynamics requires precise observations and sophisticated theoretical models. One promising approach involves statistical studies of large magnetar populations. By comparing the properties of magnetars across different environments, such as those near the galactic center, where gravitational and magnetic fields are stronger, versus those in more isolated regions, scientists might detect patterns that point to new physics. If a new force exists, its effects might vary depending on the local conditions, creating detectable differences in magnetar behavior. Magnetars and their unusual X-ray bursts. X-ray bursts from magnetars can be grouped into several categories, depending on their intensity and duration. The most common type is the short burst, which typically lasts a fraction of a second. These bursts are so powerful that they can be detected from across the galaxy, even though the actual energy release is localized to a relatively small area on the star's surface. In addition to short bursts, magnetars also produce intermediate flares, which last longer and release more energy. These events might involve a more extensive rearrangement of the star's magnetic field, possibly triggered by a larger scale movement within the crust. Intermediate flares are less common than short bursts, but offer valuable insights into the relationship between a magnetar's magnetic field and its outer layers. The energy released in these flares can heat the magnetar's surface to temperatures of millions of degrees, creating a temporary but dramatic increase in its X-ray luminosity. The most spectacular events associated with magnetars are giant flares. These are extremely rare but incredibly powerful eruptions of energy. A giant flare begins with a rapid rise in X-ray intensity, followed by a longer tail of emission that decays over several minutes. The initial peak of a giant flare is so bright that it can briefly outshine all the other X-ray sources in the galaxy combined. Giant flares are thought to originate from a catastrophic realignment of a magnetar's magnetic field. In this scenario, the intense magnetic stresses within the star's crust reach a tipping point, causing the crust to crack and releasing pent-up magnetic energy. This energy is transferred to the star's magnetosphere, accelerating particles to near-light speeds and producing the observed burst of X-rays and gamma rays. The process also generates oscillations in the star's magnetic field, which can be detected as quasi-periodic oscillations, or QPOs, in the X-ray emission. Pulsars, which are also neutron stars, primarily emit beams of radio waves and sometimes X-rays as their magnetic poles sweep across the observer's line of sight. These emissions are steady and periodic, driven by the rotation of the pulsar. Magnetars are much more chaotic. Their X-ray bursts are not tied to their rotation, but instead to the dynamic interactions between their magnetic fields and their crusts. This makes magnetars less predictable and more varied in their emissions. For pulsars, the energy comes from the gradual slowing of their rotation. As a pulsar spins down, it converts its rotational energy into electromagnetic radiation, creating a steady output over long periods. Magnetars, on the other hand, derive their energy from their magnetic fields. The decay and realignment of these fields release vast amounts of energy in bursts, which explains their sporadic and explosive nature. This magnetic energy reservoir is far greater than the rotational energy of a pulsar, enabling magnetars to produce the enormous bursts seen in giant flares. Magnetar bursts also differ from pulsar emissions in their spectral characteristics. The X-rays from magnetars often show evidence of being emitted from hotspots on their surfaces, where magnetic stresses have localized the energy release. These spots can reach temperatures of millions of degrees, much hotter than the surrounding star, and their sizes and locations can change over time. This contrasts with pulsars, whose X-ray emissions are typically associated with the acceleration of particles in their magnetospheres, producing a more uniform distribution across their surface. Some magnetars exhibit burst storms, where dozens of short bursts occur in rapid succession over hours or days. These storms suggest that the underlying magnetic stresses are distributed across multiple regions of the star's crust, triggering sequential events as one disturbance sets off another. In other cases, magnetars appear to enter quiescent states for years, showing little to no activity before suddenly erupting with a burst or flare. Magnetars' bursts are not just X-ray phenomena, they also produce gamma rays, especially during giant flares. The gamma ray emission from a giant flare can be so intense that it saturates detectors, even on spacecraft designed to observe high-energy events. For example, the giant flare from SGR 18-06-20 in 2004 was detected by multiple satellites and produced a brief but noticeable effect on Earth's ionosphere, failed supernovae. Could they be the magnetar factories? When massive stars reach the end of their lives, the cataclysmic collapse of their cores can result in a supernova. However, not all supernovae succeed in blowing apart their progenitor stars. Some stars experience what is called a failed supernova, a phenomenon where the collapse does not lead to the dramatic ejection of material. Instead, the imploding core swallows the outer layers, often resulting in the direct formation of a black hole. However, not all failed supernovae end this way. There is growing speculation that these events, under certain conditions, could produce magnetars. In a successful supernova, the energy released during the core collapse is partially transferred to the outer layers of the star, propelling them outward in an enormous explosion. The energy transfer, however, is not always efficient. If the star's mass is too great, or if its internal structure is highly stratified, the outward shockwave may not gain enough momentum to overcome the gravitational pull of the collapsing core. The result is a failed supernova, where the outer material falls back onto the core instead of escaping into space. This fallback process, while destructive, introduces conditions that could make magnetar formation more likely. When the infalling material strikes the core, it compresses it even further, creating extraordinary densities and pressures. The intense energy of this collapse can amplify any magnetic fields already present in the progenitor star, transforming them into the immensely strong fields characteristic of a magnetar. The additional material piling onto the core can also provide rotational energy, causing the newly formed neutron star to spin at incredible rates, a key ingredient in the magnetic dynamo process. As the material falls inward, it does so unevenly, creating chaotic flows of matter that can twist and stretch magnetic field lines. This process, known as the magnetorotational instability, can exponentially increase the strength of the magnetic field in just milliseconds. The result is a neutron star with a magnetic field trillions of times stronger than Earth's, capable of driving the spectacular behaviors seen in magnetars. One of the factors that might determine whether a failed supernova produces a magnetar rather than a black hole is the mass of the progenitor star's core. If the core is too massive, the gravitational forces during collapse will overcome all other pressures, resulting in the direct formation of a black hole. However, if the core's mass is within a certain range, it may stabilize as a neutron star, allowing the processes that create magnetars to occur. This sweet spot in core mass could explain why magnetars are relatively rare compared to other neutron stars and black holes. The environment surrounding a failed supernova might also contribute to magnetar formation. In some cases, the infalling material could generate additional shocks or turbulence as it interacts with the collapsing core. These interactions might introduce asymmetries in the magnetic field, further strengthening it. The fallback material could also supply fresh fuel for accretion, creating a short-lived but intense period of energy release that powers the young magnetar's emissions. Failed supernovae might explain why magnetars are often found in regions of the galaxy where massive stars have recently died. These regions, known as star-forming clusters, are rich in young massive stars that are likely candidates for failed supernovae. The presence of magnetars in these environments suggests a connection between the life cycles of massive stars and the extreme conditions needed for magnetar formation. These events are difficult to detect because they do not produce the bright explosions characteristic of successful supernovae. Instead, they may emit only a faint burst of neutrinos or a brief pulse of gravitational waves as the core collapses. Identifying the remnants of these events, such as young magnetars, requires careful analysis of their environments and properties. One example that supports the connection between failed supernova and magnetars is the Magnetar SGR 1900+14, which is located near a cluster of massive stars. This magnetar's proximity to a region rich in progenitor stars suggests that it may have formed from a failed supernova. Similar cases have been observed for other magnetars, reinforcing the idea that these objects are born from the most massive and extreme stars. The influence of companion stars on magnetar birth. In binary star systems, the close interaction between two stars can profoundly influence the life cycles of both, and this interplay becomes especially critical during the late stages of their evolution. For a star destined to become a magnetar, its companion may alter its magnetic field, spin rate, or mass, creating conditions that enhance or potentially prevent the development of a magnetar. In a binary system, stars are gravitationally bound, often exchanging material and angular momentum as they evolve. If one of the stars is much larger than the other, it will reach the end of its life more quickly, swelling into a red supergiant and potentially transferring mass to its smaller companion. This mass transfer can strip the outer layers of the larger star, exposing its core and accelerating its evolution toward a core collapse supernova. The removal of the outer layers might also reduce the overall mass of the star, potentially keeping the core within the range necessary for neutron star formation, rather than collapsing into a black hole. This stripped-down core, spinning faster due to the conservation of angular momentum, could then become a magnetar. When mass flows from one star to another, it carries angular momentum, which can either speed up or slow down the rotation of the accreting star. For a magnetar to form, rapid rotation is a key ingredient. Faster rotation during the collapse phase helps amplify the star's magnetic field through dynamo processes, creating the extreme fields characteristic of magnetars. In some cases, the presence of a companion star might supply just enough angular momentum to spin up the progenitor star to the required rate. On the other hand, in more extreme cases of mass transfer, a companion star might actually spin down the magnetar progenitor, disrupting the conditions necessary for its formation. The degree of influence depends on the binary system's orbital configuration, the star's initial masses, and the timing of the mass transfer. Close binary systems, where the stars are separated by only a few solar radii, are more likely to experience significant interactions that could dramatically alter the fate of the progenitor. During the later stages of stellar evolution, as the progenitor star begins to collapse, its magnetic field may interact with the magnetic field or stellar winds of the companion. These interactions could lead to a complex reshaping of the magnetic environment, potentially boosting the progenitor's field strength. For example, magnetic reconnection events, where magnetic field lines from the two stars collide and reconfigure, might inject additional energy into the system. Binary systems that involve compact objects, such as a neutron star or white dwarf orbiting the magnetar progenitor, offer even more intriguing possibilities. If the companion is a neutron star, its gravitational influence could create tidal forces within the progenitor, generating internal friction and heat. These tidal interactions might drive mixing within the progenitor's core, altering its magnetic field structure and possibly enhancing it. Additionally, the gravitational pull from the companion could influence the shape of the collapsing star, potentially introducing asymmetries that further strengthen the magnetic field during the core collapse phase. In some cases, the presence of a compact companion might also lead to episodes of episodic mass accretion before the final collapse. These episodes could cause bursts of angular momentum to be deposited into the progenitor's core, spinning it up in fits and starts. This erratic rotation could amplify the magnetic field in ways that differ from isolated stars, creating magnetars with unique properties compared to those formed in single-star systems. Systems with very tight orbits may experience a phase of common envelope evolution, where the expanding outer layers of the progenitor engulf the companion star. This phase is highly chaotic, with the companion spiraling inward as it loses angular momentum to the shared envelope. The energy released during this process can strip away even more of the progenitor's outer layers, exposing its core and potentially spinning it up further. If the progenitor survives this phase without collapsing prematurely, the stripped and rapidly rotating core could become a prime candidate for magnetar formation. In wider binary systems, where the stars are farther apart, the interactions may be less dramatic but still significant. For instance, stellar winds from the companion could influence the magnetic environment of the progenitor. Strong winds might compress the progenitor's magnetic field, enhancing its intensity and shaping the conditions for magnetar birth. Additionally, if the companion itself undergoes supernova-like events or sheds material, this external influence could indirectly impact the progenitor's evolution. Observations of magnetars in binary systems are relatively rare. In a few cases, magnetars have been found in systems with massive companion stars, suggesting that the companion may have played a role in their formation. These systems often exhibit unusual orbital dynamics or peculiar chemical compositions, hinting at a history of intense interaction between the two stars. One well-studied example is the Magnetar 1e 2259 plus 586, located in the Cassiopeia constellation. While it is not definitively part of a binary system, its surrounding environment and unusual properties suggest a history of interaction with another star. If future observations confirm the presence of a companion, it could provide valuable insights into how binary interactions contribute to magnetar formation. Theoretical models support the idea that binary systems might be magnetar factories. Simulations of binary star evolution show that mass transfer and angular momentum exchange can create conditions favorable for magnetar birth. These models suggest that binary interactions could account for a significant fraction of the magnetar population, particularly those with extremely high magnetic fields or unusual spin rates. Despite the progress in understanding these processes, many questions remain. For instance, it is unclear why some binary interactions lead to magnetars, while others result in typical neutron stars or even black holes. The role of initial magnetic field strength, the timing of mass transfer, and the details of angular momentum exchange are all areas of active research. Observations of young binary systems and the remnants of failed supernova could help answer these questions. The 2004 Magnetar Flare, Earth's Close Encounter. In December 2004, an extraordinary cosmic event unfolded, briefly drawing attention to the immense power of magnetars. A sudden and colossal flare from SGR 1806-20, a magnetar located about 50,000 light-years away in the constellation Sagittarius, reached Earth. This was not just another distant astronomical phenomenon. The giant flare was so intense that it briefly overwhelmed detectors on satellites and had a measurable impact on Earth's atmosphere. SGR 1806-20 is a soft gamma repeater, a type of magnetar known for emitting bursts of gamma rays and X-rays sporadically. However, what occurred on December 27, 2004, far exceeded its usual behavior. Without warning, the magnetar unleashed an immense burst of energy. For a fraction of a second, it was the brightest source of gamma rays in the sky, briefly outshining the rest of the Milky Way combined. Even from 50,000 light-years away, the flare delivered enough energy to affect Earth's upper atmosphere. The energy released in this single event was staggering. In just 0.2 seconds, the Magnetar emitted as much energy as the Sun produces in 100,000 years. The flare consisted of an initial spike of gamma rays, followed by a longer-lasting tail of lower-energy radiation. The initial spike was so powerful that it saturated gamma-ray detectors on several space observatories, including NASA's RESI satellite and the Swift Gamma-Ray Burst mission. Scientists later reconstructed the data to estimate the flare's intensity, but the precise figures remain somewhat uncertain due to the overwhelming scale of the event. When the flare reached Earth, it interacted with our planet's ionosphere, the outermost layer of the atmosphere that is ionized by solar radiation. Typically, changes in the ionosphere are driven by solar activity, such as solar flares and coronal mass ejections. However, the SGR 1806-20 flare provided a rare opportunity to observe how an external gamma-ray burst could influence the ionosphere. Instruments on Earth detected a sudden and dramatic increase in ionization levels, particularly in the lower ionosphere. This ionization surge temporarily disrupted radio communications, a phenomenon similar to what happens during strong solar flares. The effects on the ionosphere were detected by very low-frequency VLF radio wave monitoring stations. These stations track changes in the ionosphere by observing how VLF radio waves propagate. The arrival of the Magnetar's flare altered the behavior of these waves, providing scientists with direct evidence of the ionosphere's response to the burst. While the disruption was short-lived and did not cause any lasting harm, it highlighted the potential for Magnetar flares to interfere with technological systems on Earth, potentially catastrophically. Despite its immense energy, the flare posed no direct danger to life on Earth. The planet's thick atmosphere and magnetic field shielded the surface from the high-energy radiation. However, if such an event were to occur from a Magnetar much closer to Earth, within a few light-years, the consequences would be far more severe. High doses of gamma rays and X-rays would damage the ozone layer, exposing life on the surface to harmful ultraviolet radiation from the Sun. The potential effects on global communications, satellites, and power grids would also be significant, given the sensitivity of modern infrastructure to electromagnetic interference. It would undoubtedly trigger a new mass extinction. The 2004 event provided a wealth of data that scientists have used to study Magnetar flares and their effects. One of the key questions it raised was what causes such powerful outbursts. While the exact mechanisms remain under investigation, many scientists believe that the giant flare was triggered by a starquake. The flare from SGR 1806-20 prompted discussions about the frequency of such events. While giant flares are thought to be rare, they may be more common than previously believed, especially in the early history of the universe when massive stars were more abundant. Observations of other galaxies suggest that similar flares occur regularly, but their detection depends on their distance and orientation relative to Earth. Magnetars, with their magnetic poles aimed directly at Earth, are more likely to produce observable effects. The 2004 flare also emphasized the importance of monitoring gamma-ray bursts and magnetars as part of space weather research. While the immediate impacts of the flare were limited, it served as a reminder of the unpredictable nature of the cosmos. Efforts to improve gamma-ray detection and ionospheric monitoring have since become more critical, as scientists seek to understand and mitigate the potential risks posed by extreme astronomical events. If a similar event were to occur near another star system, it could have profound effects on any planets within the vicinity. By studying such flares, scientists can gain insight into the potential hazards faced by planets orbiting stars with active magnetars nearby. How magnetars disrupt local space-time. The influence of magnetars is not limited to the particles and light in their vicinity. The sheer power they unleash may have subtle yet measurable effects on the very fabric of space-time itself. These effects, though difficult to detect, offer a glimpse into how such cosmic giants interact with the underlying structure of the universe. The concept of space-time comes from Einstein's theory of general relativity, which describes gravity as the curvature of space and time caused by mass and energy. Massive objects like stars and black holes bend space-time, and any changes in their behavior can create ripples known as gravitational waves. While magnetars are not as massive as black holes, their extraordinary magnetic fields and violent outbursts introduce unique factors that could distort space-time in their local environment. The first key element to consider is the strength of a magnetar's magnetic field. At their peak, these fields can reach up to a quadrillion Gauss, far exceeding anything else in the universe. For comparison, Earth's magnetic field is roughly half a Gauss, and even the strongest magnets humans can create are only tens of thousands of Gauss. Magnetars' fields are so powerful that they can influence the quantum vacuum surrounding them, polarizing empty space and affecting how light travels. This alteration of light paths hints at a deeper interaction with space-time, as the magnetic field pushes the limits of physical laws in its vicinity. During a Magnetar outburst, the energy released is colossal. This energy doesn't just radiate outward as light or particles, it also carries momentum and pressure. The sudden release of such energy can generate forces strong enough to shake the magnetar's structure, potentially causing oscillations in its dense interior. These oscillations, in turn, might ripple through space-time, creating gravitational waves that propagate outward. Gravitational waves are produced when massive objects undergo rapid asymmetric changes in their distribution of mass or energy. Magnetars are prime candidates for creating these waves due to their dynamic activity. For instance, when a starquake fractures a magnetar's crust, the resulting rearrangement of mass and energy could produce a burst of gravitational waves. The violent magnetic reconnection events associated with giant flares might also contribute to these ripples. The structure of a magnetar itself may also amplify its impact on spacetime. Neutron stars are incredibly dense, and this density creates an intense gravitational field that already curves spacetime significantly. When combined with the magnetar's dynamic magnetic activity, this curvature might experience local fluctuations during energetic events. These interactions could produce unique gravitational signatures, distinguishing magnetars from other types of neutron stars. Their immense energy output, especially during giant flares, can create shock waves in surrounding plasma and accelerate particles to nearly the speed of light. These high-energy particles, interacting with the curved spacetime around the magnetar, could produce detectable signals in other wavelengths, such as gamma rays or radio waves. Over long periods, their intense magnetic fields could interact with the surrounding interstellar medium, shaping its structure and creating magnetized bubbles or filaments. These features, detectable through radio or X-ray observations, would serve as evidence of the magnetar's impact on its surroundings. The cumulative effects of many such objects in a galaxy could contribute to large-scale magnetic fields, linking magnetars to broader cosmic structures. Theoretical models suggest that magnetars with certain rotational or magnetic configurations might produce particularly strong space-time distortions. For example, rapidly rotating magnetars, sometimes called hypermagnetars, could combine their magnetic and rotational energies to create highly energetic outbursts. These events might amplify gravitational wave production. Such scenarios could help scientists understand how rotation and magnetism interact to influence a neutron star's overall behavior. If a magnetar orbits another massive object, such as a black hole or another neutron star, their gravitational interaction could enhance the production of gravitational waves. The magnetar's magnetic activity might add complexity to these signals, creating patterns that differ from those of typical binary mergers. Beyond their role as sources of gravitational waves, magnetars provide a way for testing the limits of general relativity and quantum field theory. Their extreme conditions challenge our models, pushing them to account for phenomena that occur nowhere else in the universe. Observations of magnetar-related distortions in spacetime could provide critical data for refining these theories or even discovering new physics. The energy budget of a magnetar flare. Magnetar flares release colossal amounts of energy within mere seconds. To understand the energy budget of a magnetar flare, it is important to grasp the scale of these outbursts and the processes that power them. These flares are not only immense in their energy output, but also influence their surroundings in profound ways, from damaging nearby objects to altering entire planetary systems. The most basic metric to grasp is the sheer magnitude of energy released during a magnetar flare. Giant flares can emit energy equivalent to hundreds of thousands of years of solar output in just a fraction of a second. For context, the Sun produces about 10 to the power of 26 joules of energy per second. A single giant flare from a magnetar can reach 10 to the power of 44 joules, dwarfing the total energy produced by the Sun over its lifetime. This energy output is so vast that it can momentarily outshine an entire galaxy when viewed in high-energy wavelengths like X-rays and gamma rays. The energy released during a magnetar flare is thought to originate from the star's immense magnetic field. Magnetars harbor fields as strong as 10 to the power of 15 Gauss, capable of storing vast amounts of magnetic energy. These fields are highly dynamic and prone to instabilities. When the stress in the magnetic field exceeds the structural limits of the star's crust, it can trigger a catastrophic release of energy. This release comes in the form of electromagnetic radiation, relativistic particles, and seismic waves that ripple through the star itself. The bulk of a magnetar flare's energy is emitted as high-energy photons, predominantly X-rays and gamma rays. These photons travel at the speed of light, radiating outward and illuminating the surrounding space. The intensity of this radiation can be devastating for any nearby celestial objects. Planets within a few light-years of a magnetar flare would experience severe consequences. Their atmospheres could be stripped away, and their surfaces irradiated with lethal doses of high-energy radiation. For unshielded life forms, such an event would be catastrophic. In addition to electromagnetic radiation, magnetar flares also release streams of highly energetic particles. These particles, including protons and electrons, are accelerated to near-light speeds by the magnetic field. The resulting particle wind can interact with nearby interstellar material, creating shock waves that propagate outward. These shock waves can heat and compress gas, potentially triggering star formation in some regions while dispersing gas clouds in others. The influence of these particle streams on nearby planetary systems would depend on their intensity and duration. A sustained barrage of particles could damage magnetic fields, disrupt electronics, or even erode planetary surfaces. The immediate vicinity of a magnetar flare, within a few 100,000 kilometers, is a zone of extreme violence. Any objects located there would be vaporized almost instantly by the intense heat and radiation. At greater distances, the impact would depend on the flare's energy and the shielding provided by an object's magnetic field or atmosphere. For instance, a planet with a strong magnetic field might be able to deflect some of the incoming particle radiation, reducing the overall damage. However, the X-rays and gamma rays would still penetrate, heating the atmosphere and causing chemical reactions that could alter its composition. One striking example of a magnetar flare's impact is the 2004 event from SGR 1806-20, which released an estimated 10 to the power of 39 joules of energy. This flare was powerful enough to ionize Earth's upper atmosphere, even though the magnetar was located over 50,000 light-years away. Had this flare occurred within a few light-years of Earth, the effects would have been devastating, potentially overwhelming our planet's magnetic field. The energy released during a magnetar flare also includes mechanical effects within the star itself. The intense magnetic stress can fracture the crust of the magnetar, creating starquakes. These seismic events release energy in the form of oscillations which can propagate through the star and even into surrounding space as gravitational waves. The radiation and particle wind from a flare could strip material from a companion star, altering its evolution. In extreme cases, the flare could disrupt the binary system entirely, ejecting the companion star or causing it to spiral into the magnetar. The energy injected into the interstellar medium by a flare can compress and heat gas clouds, creating conditions conducive to star formation. The shock waves from the flare's particle wind can also sweep up material, forming shells or bubbles that become visible in radio or X-ray wavelengths. These features serve as lasting reminders of the magnetar's activity, shaping the structure of the galaxy on scales far larger than the star itself. Magnetars and interstellar gas clouds, shaping the environment. Magnetars are not just cosmic spectacles. They actively interact with their surroundings, shaping the environment in ways that leave lasting imprints on the galaxy. This includes interstellar gas clouds, vast reservoirs of gas and dust that are the raw material from which stars and planetary systems are born. When a magnetar releases its energy, whether through steady emissions or explosive outbursts, the impact on nearby gas clouds can be dramatic, potentially altering the course of star formation and reshaping the structure of the interstellar medium. The interaction begins with the high-energy radiation emitted by magnetars. These events release a torrent of X-rays and gamma rays capable of traveling vast distances through space. When this radiation encounters an interstellar gas cloud, it ionizes the atoms within, stripping electrons from their nuclei. This ionization process can heat the gas, increasing its thermal pressure and altering its dynamics. Ionized gas behaves differently from neutral gas, becoming more susceptible to magnetic fields and less prone to clumping together under gravity. As a result, the ionization caused by a magnetar outburst can delay or even prevent the formation of new stars within a cloud. In some cases, the radiation from a magnetar can compress a gas cloud rather than disperse it. This occurs when the energy from the outburst creates shock waves that propagate through the surrounding medium. These shock waves, composed of high-energy particles and radiation, sweep up gas and dust as they travel, compressing the material into denser regions. This compression can trigger the collapse of parts of the cloud, initiating the formation of new stars. The balance between ionization and compression depends on factors such as the intensity of the outburst, the distance of the gas cloud from the magnetar, and the initial conditions within the cloud itself. Magnetar flares are particularly effective at driving such interactions because of their sheer intensity. A single giant flare can release more energy than a typical supernova, albeit over a much shorter timescale. The particles accelerated during the flare, including protons and electrons, add to the energy budget and play their own role in shaping the interstellar environment. These particles, moving at nearly the speed of light, collide with gas atoms in the cloud, producing secondary radiation and further heating the gas. The cumulative effect of these processes can transform a previously quiescent gas cloud into a hotbed of activity. The scale of a magnetar's influence on interstellar gas is not confined to its immediate surroundings. The energy from a powerful outburst can travel across many light years, impacting multiple gas clouds and regions of space. Observations of supernova remnants and other energetic phenomena often reveal evidence of such interactions, such as ionized gas filaments or shockwave-driven shells. These structures serve as markers of the magnetar's presence, even if the star itself is no longer active or visible. When a shockwave compresses a gas cloud, it can create conditions favorable for the rapid accumulation of material, leading to the birth of stars much larger than the Sun. These massive stars, in turn, have short lifespans and end their lives in supernovae, potentially giving rise to new magnetars. In this way, magnetars can contribute to a cycle of star formation and destruction, influencing the evolution of their galactic environments over millions of years. Magnetars can also impact the chemical composition of interstellar gas clouds. The intense radiation from an outburst can break apart molecules within the cloud, a process known as photodissociation. This alters the mix of chemical species in the cloud, potentially affecting the types of stars and planets that form there. For example, the destruction of complex organic molecules could reduce the likelihood of forming planets with conditions suitable for life. On the other hand, the radiation could also create new chemical pathways, leading to the synthesis of molecules that would not otherwise form. The net effect of a magnetar's influence on the chemistry of a gas cloud is complex and depends on the interplay of various factors, including the duration and intensity of the radiation. The magnetic fields of magnetars extend far beyond the star itself and can exert forces on nearby gas clouds, altering their motion and structure. A strong magnetic field can channel ionized gas along specific paths, creating filaments or streams within the cloud. These structures are often observed in regions of active star formation, where magnetic fields play a crucial role in shaping the dynamics of the gas. In the case of a magnetar, the magnetic influence can extend over large distances, potentially affecting multiple gas clouds. Magnetars are thought to contribute to the overall magnetic field of the galaxy, which influences the behavior of interstellar gas on a grand scale. By injecting energy and magnetic flux into the interstellar medium, magnetars help to maintain the turbulent conditions that characterize many regions of the galaxy. This turbulence, in turn, affects the distribution of gas and the rate of star formation, highlighting the interconnectedness of magnetars and their surroundings. In some cases, the influence of a magnetar on a gas cloud can lead to the formation of unusual or exotic structures. For instance, the interaction of a magnetar's outburst with a dense molecular cloud could create a luminous shockwave visible in radio or X-ray wavelengths. These features, known as magnetar wind nebulae, are relatively rare but provide valuable insights into the energy output and environmental impact of magnetars. Magnetic field lines, how they store and release energy. The magnetic field lines that weave through a magnetar's surroundings act like taut rubber bands under immense tension. When these field lines twist, tangle, or break, the stored energy can be unleashed in dramatic and explosive events. Understanding how magnetic field lines store and release energy is key to unraveling the mysteries of Magnetar outbursts and their devastating effects. Magnetic field lines are visual representations of how magnetic forces are arranged around a star. They don't physically exist, but are useful for understanding the behavior of magnetic forces in space. In a magnetar, these field lines are unimaginably intense, tightly coiled, and often highly distorted by the star's rotation and internal activity. The energy stored in these lines is vast, held in the form of magnetic tension and pressure. This energy can remain dormant for long periods, but when the field becomes unstable, it can release its energy in a fraction of a second, producing bursts of radiation that can travel across the galaxy. One of the most significant processes behind the release of magnetic energy is magnetic reconnection. This phenomenon occurs when magnetic field lines break apart and reconnect in a new configuration. On the Sun, magnetic reconnection drives solar flares and coronal mass ejections, events that release vast amounts of energy and can disrupt space weather near Earth. In magnetars, the same process occurs on a far grander scale. Magnetic reconnection begins when field lines, typically under tension, are forced together by shifting currents within the magnetar's magnetic field. These currents are driven by various factors, including movements in the star's crust and changes in its internal magnetic structure. When field lines come into close proximity, their opposing directions can create instability. At the point of contact, the lines break and reattach to one another, forming new, simpler configurations. This rearrangement releases the energy stored in the original tangled configuration, often in the form of high-energy radiation and charged particles. The release of energy during reconnection is sudden and explosive, much like snapping a tightly wound rubber band. The particles near the reconnection site are rapidly accelerated, creating a cascade of high-energy photons in the form of X-rays and gamma rays. In the case of magnetars, this process can trigger giant flares. The trigger for magnetic reconnection in a magnetar often comes from within the star itself. The crust of a magnetar, though rigid, can only withstand so much pressure before it cracks or shifts. These starquakes can displace the magnetic field lines anchored in the crust, forcing them into new, unstable configurations. The resulting reconnection events can escalate rapidly, producing bursts of energy that we observe as Magnetar outbursts. The reconnection process is incredibly efficient at converting magnetic energy into other forms, making magnetar flares some of the brightest events in the cosmos. Reconnection events in magnetars are not uniform. They can vary in size and intensity, depending on the complexity and tension of the magnetic field lines involved. Smaller reconnection events may produce short bursts of X-rays, while larger, more catastrophic events can trigger gamma-ray bursts visible across billions of light-years. While solar flares can be observed in great detail with telescopes and spacecraft, magnetars are too distant for such precise measurements. Instead, astronomers rely on indirect evidence, such as the timing, intensity, and spectrum of the radiation produced during an outburst. By comparing these observations to models of magnetic reconnection, researchers can infer the conditions and processes driving these events. The magnetic fields of magnetars are so strong that they can influence the properties of the space around them, creating regions where reconnection is more likely to occur. These regions, known as current sheets, are thin layers of intense magnetic stress. Current sheets form naturally in dynamic magnetic fields and serve as hotspots for reconnection. In a magnetar, These sheets can extend over large areas, providing multiple sites for energy release during an outburst. The aftermath of a reconnection event is just as fascinating as the event itself. Once the field lines have rearranged, the magnetic field temporarily stabilizes, reducing the stress on the magnetar's crust. However, this stability is often short-lived. The star's internal dynamo processes, which continuously generate and sustain its magnetic field, can reintroduce complexity and tension, setting the stage for future reconnection events. This cycle of stress, reconnection, and relaxation is a defining characteristic of magnetars and explains their sporadic and unpredictable behavior. Are magnetars responsible for fast radio bursts? Fast radio bursts, or FRBs, are incredibly brief and intense flashes of radio waves, lasting only milliseconds, that have puzzled astronomers since their discovery in 2007. What makes them so intriguing is their enormous energy. In just a fraction of a second, an FRB can release as much energy as the Sun does in days. While many theories have emerged to explain their origins, one of the most compelling ideas links them to magnetars. Recent observations have strengthened this connection, pointing to these magnetic titans as possible culprits behind these enigmatic signals. Magnetars are known for their ability to produce sudden, violent bursts of energy. These bursts are typically observed in the X-ray or gamma-ray spectrum, but their underlying mechanisms could also generate radio waves. The idea that magnetars might produce FRBs gained traction after the discovery of FRBs with repeating patterns. Unlike one-off FRBs, which might originate from catastrophic events like the collapse of a star, repeating FRBs suggest a source capable of producing multiple bursts over time. Magnetars, with their unstable magnetic fields and periodic outbursts, fit this description well. In 2020, the link between magnetars and FRBs became more concrete. Astronomers detected a fast radio burst from a known magnetar in our galaxy, SGR 1935 plus 2154. This event, labeled FRB 200428, was the first time an FRB had been directly associated with a specific source. The magnetar had already been observed producing X-ray bursts, and the timing of the radio burst aligned with one of these high-energy events. While this FRB was weaker than those typically detected from distant galaxies, it provided a critical piece of evidence connecting magnetars to the phenomenon. The mechanism behind how magnetars might produce FRBs involves their powerful magnetic fields and the processes that occur during outbursts. One leading theory suggests that during a starquake, the magnetar's crust cracks and shifts under immense magnetic stress. This sudden movement can release energy in the form of electromagnetic waves, including radio waves. In this model, the intense magnetic environment of the magnetar accelerates particles to nearly the speed of light, generating coherent radio emissions that travel across space. Another theory focuses on the magnetar's magnetosphere, the region dominated by its magnetic field. As the magnetic field lines shift and reconnect, they can release bursts of energy. In some cases, the energy released during reconnection could include powerful radio waves. These waves, amplified by the magnetar's extreme environment, could explain the brief but intense nature of FRBs. A more speculative idea involves the interaction of a magnetar with surrounding material. Some magnetars are located in dense environments, such as remnants of supernova explosions. When a magnetar emits a burst of energy, it could collide with this surrounding material, creating shockwaves that produce radio emissions. These emissions might resemble FRBs in their intensity and duration. Observing the environments of magnetars associated with FRBs could help test this hypothesis. The discovery of repeating FRBs has added complexity to the magnetar connection. Some repeating FRBs show patterns in their bursts, with intervals ranging from hours to days. This periodicity suggests that the source might be influenced by external factors, such as interactions with a companion star or orbiting debris. Magnetars, in binary systems, could provide a natural explanation. As the magnetar orbits its companion, the changing magnetic environment could trigger bursts at regular intervals. Alternatively, material from the companion star could fall onto the magnetar, sparking radio emissions. Some FRBs are so powerful that they challenge our understanding of how magnetars could produce them. While typical magnetar flares release immense energy, the processes involved in generating FRBs might require even more extreme conditions. This has led some researchers to propose that only the youngest and most energetic magnetars, with the strongest magnetic fields, can produce FRBs. Observations of young magnetars in distant galaxies could help test this idea. FRBs observed from distant galaxies pose another puzzle. These bursts often show signatures of passing through dense material, which distorts their signals. This suggests that the sources of these FRBs are located in environments rich in gas and dust. Magnetars, which are often found in such environments due to their origins in supernovae, are a natural fit. Despite the growing evidence linking magnetars to FRBs, not all bursts can be easily explained by this model. Some FRBs show properties that differ from those associated with magnetars, such as unusual polarization or longer durations. This has led to the possibility that FRBs might have multiple origins. While magnetars could account for many FRBs, other sources, such as neutron star mergers or black hole interactions, might be responsible for the rest. Radio telescopes like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, have greatly expanded our ability to detect FRBs, uncovering hundreds of new events. These observations have revealed a wide diversity in FRB properties, from single bursts to repeating patterns, and have helped identify potential connections to magnetars. Future telescopes promise to provide even greater sensitivity and resolution, allowing astronomers to pinpoint the locations of FRBs with unprecedented precision. The most powerful magnetars ever observed. Among the many known magnetars, a few stand out as the most extreme, their power defying even the extraordinary norms of these celestial objects. These magnetars have been observed to release energy at levels that stretch our understanding of physics, offering a rare glimpse into the upper limits of what these objects can do. One of the most famous and powerful magnetars ever observed is SGR 1806-20, located about 50,000 light-years from Earth in the constellation Sagittarius. This magnetar achieved global fame following its giant flare on December 27, 2004, one of the most energetic events ever recorded in the galaxy. The flare released more energy in a fraction of a second than the Sun produces in 100,000 years. At its peak, the flare emitted gamma rays at a brightness level briefly exceeding that of the full moon in the sky, even though the magnetar was thousands of trillions of kilometers away. Detectors on Earth and in space were overwhelmed by the event. SGR 1806-20's flare showcased the energy stored in its magnetic field, estimated to be over 10 to the power of 15 Gauss, roughly a quadrillion times stronger than the magnetic field at Earth's surface. While giant flares like this are rare, their occurrence underscores the fact that some magnetars operate at or near the theoretical limits of magnetic energy storage. Another notable example is one E1048.1-5937, a magnetar that has shown some of the most diverse activity ever recorded, including erratic bursts, long-term X-ray variability, and transient radio emissions. Located in the Carina constellation, this magnetar's activity patterns challenge models of how magnetic energy dissipates over time. Its behavior suggests that some magnetars may store energy in ways not yet fully understood, allowing for sudden bursts of power that seem disproportionate to their gradual energy decay rates. Observations of this magnetar raise intriguing questions about what factors influence a magnetar's lifetime activity and how some might maintain their extreme outputs for millions of years. In the same league is PSRJ 1745-2900, a magnetar located surprisingly close to the supermassive black hole at the center of the Milky Way. This magnetar is unique because of its environment, as the intense gravitational and electromagnetic fields near the black hole make it an exceptional laboratory for studying extreme physics. Despite its challenging observational conditions, due to its proximity to the galactic center's dense and turbulent environment, this magnetar has provided valuable insights into how magnetars interact with their surroundings. Its magnetic field strength, estimated at over 10 to the power of 14 Gauss, positions it among the most powerful magnetars known. The combination of its magnetic strength and its location near Sagittarius A** has prompted speculation about whether interactions with the black hole's environment might influence its activity. A particularly enigmatic magnetar is Swift J1818.0-1607, discovered in 2020. This magnetar is remarkable not only for its extreme magnetic field, but also for its youth, estimated to be only 240 years old, making it one of the youngest magnetars ever identified. Its magnetic field strength, calculated at over 10 to the power of 15 Gauss, places it near the upper boundary of what current models predict for neutron star magnetism. Its youth and extreme properties suggest it may represent an early stage in the evolution of magnetars, where their magnetic fields are still highly active and capable of producing frequent powerful outbursts. Observing such a young magnetar offers an unprecedented opportunity to study the formation and early behavior of these objects, shedding light on how their magnetic fields are generated and evolve over time. Beyond these specific cases, some theoretical models suggest the existence of hypermagnetars, objects with magnetic fields even more extreme than those observed so far. While no such magnetars have been confirmed, their theoretical properties push the boundaries of physics. Hypermagnetars could potentially have magnetic fields exceeding 10 to the power of 16 Gauss, powerful enough to influence even the fundamental structure of matter. Such objects might only form under the most extreme conditions, such as in failed supernovae or through binary neutron star mergers. If they exist, hypermagnetars would likely produce outbursts and emissions orders of magnitude beyond anything observed, potentially explaining the most energetic fast radio bursts or other enigmatic cosmic phenomena. When comparing these magnetars to theoretical limits, certain questions arise. How much magnetic energy can a neutron star's structure physically sustain before collapsing under its own forces? Current models suggest that magnetic fields exceeding a few times 10 to the power of 15 Gauss could begin to destabilize the neutron star's crust or core. However, the observations of magnetars near these limits and their ability to produce recurrent flares suggest that they may have mechanisms for dissipating energy without catastrophic failure. These mechanisms might involve gradual untwisting of magnetic field lines, releasing energy in bursts rather than all at once. Many of the strongest magnetars are believed to have been born as rapidly spinning neutron stars with rotation periods of a few milliseconds. This rapid rotation during formation likely amplified their magnetic fields through a dynamo process, allowing them to reach the extraordinary field strengths observed today. Over time, as they lose rotational energy and spin more slowly, these magnetars continue to release their stored magnetic energy, producing the spectacular outbursts that make them so fascinating. How magnetar flares could affect nearby planetary systems. When a magnetar releases a flare, the energy it emits can rival or exceed that of an entire galaxy for a few moments. This energy primarily takes the form of high-energy radiation, such as X-rays and gamma rays, but it also includes charged particles and intense magnetic waves. If a planet was situated within a few light-years of a magnetar, these emissions could be devastating. The atmosphere of the planet would likely be the first to feel the effects. High-energy gamma rays and X-rays can ionize atmospheric molecules, breaking them apart into charged particles. Over time, this process could erode the atmosphere, stripping it away and leaving the planet exposed to the harsh radiation of space. On Earth, the atmosphere serves as a shield, absorbing harmful radiation and protecting the surface. However, a planet too close to a magnetar might experience such intense radiation that even a thick atmosphere wouldn't offer enough protection. Layers of the atmosphere, such as the ozone layer, could be destroyed, removing the barrier that blocks harmful ultraviolet radiation from a planet's star. The consequences for any life on the planet could be catastrophic, ranging from widespread mutations due to increased radiation exposure to the collapse of ecosystems dependent on atmospheric stability. Beyond atmospheric erosion, the charged particles ejected during a magnetar flare could interact with a planet's magnetic field, if it has one. Planetary magnetic fields act as shields against solar wind and cosmic particles, but the magnetic waves produced by a magnetar flare would be orders of magnitude stronger than anything most planetary fields are designed to handle. These waves could compress or even destabilize the magnetic field, exposing the planet's surface to radiation and particle bombardment. For planets with weak or non-existent magnetic fields, the damage could be even more severe, with charged particles directly striking the surface and potentially altering its chemical composition. The destruction caused by a magnetar flare wouldn't stop at the planet's surface. The radiation could penetrate deep into the planet's crust, disrupting geological processes and possibly triggering seismic activity. On planets with subsurface oceans, such as some moons in our solar system, the heat generated by such intense radiation might lead to the rapid expansion of subsurface water, causing violent eruptions or other surface changes. The long-term impact could reshape the planet's environment entirely, leaving it unrecognizable from its pre-flare state. For planetary systems hosting magnetars, the zone of potential habitability may be drastically altered. In a typical star system, planets orbiting at a certain distance from the star, the so-called habitable zone, have the right conditions for liquid water to exist. But in systems with a magnetar, the bursts of radiation could sterilize planets even within this zone. The proximity required for a planet to experience the full brunt of a magnetar flare means that such systems are unlikely to host life as we know it, unless organisms there have evolved extraordinary resilience to radiation. For planets with advanced civilizations, the implications of a nearby magnetar flare would extend beyond the immediate physical damage. Societal infrastructure, heavily dependent on technology and communication systems, could collapse under the strain of a prolonged disruption. High-energy radiation could fry electronic components in satellites and spacecraft, rendering entire networks inoperable. Without reliable means of communication and navigation, modern societies would face unprecedented challenges. The potential for life to survive on planets near magnetars depends on several factors, including the frequency of flares, the strength of the planet's magnetic field, and the resilience of any existing ecosystems. Life in such environments would likely be very different from what we are familiar with, potentially existing underground or in deep oceans where the radiation cannot penetrate. Microorganisms might evolve radiation-resistant adaptations, similar to certain extremophiles on Earth that thrive in high radiation environments like nuclear reactors. However, the repeated, unpredictable bursts from a magnetar would create an unstable environment, making the long-term survival of complex life highly unlikely. Magnetars as cosmic terraformers. Can their energy jumpstart dead planets? Though magnetars are seen as cosmic destroyers, with their immense energy and magnetic fields, what if, under certain conditions, their energy could serve as a creative force rather than a destructive one? Could the outbursts of a magnetar, rich in radiation and charged particles, play a role in revitalizing dormant planets, reshaping atmospheres, or even reigniting planetary cores? When a magnetar releases a burst of energy, it unleashes a cocktail of electromagnetic radiation, high-energy particles, and magnetic forces. These bursts can travel vast distances, spreading their influence across light years. For planets within the range of these emissions, the effects can be profound. While the immediate impact might be harmful, such as stripping away parts of an atmosphere or irradiating the surface, there are scenarios where these forces could set off a chain of processes that might ultimately be beneficial to a planet's evolution. One way this could happen is through atmospheric reshaping. Planets with thin or no atmospheres might experience a temporary thickening or transformation of their atmospheric layers when subjected to the ionizing effects of a magnetar's energy. High-energy radiation from the magnetar could break apart stable molecules in a planet's surface or subsurface layers, releasing gases like oxygen, nitrogen, or carbon dioxide. If these gases accumulate, they could form a new atmosphere or replenish an existing one. For planets on the edge of habitability, this process might even help stabilize surface temperatures or create conditions suitable for the presence of liquid water. On planets with dormant or weak magnetic fields, the intense magnetic energy from a magnetar could theoretically induce electric currents in the planet's core or mantle. This electromagnetic induction has been studied in other contexts, such as the interaction between planetary magnetic fields and solar winds. A powerful external magnetic field could excite the motion of conductive materials within a planet, potentially reigniting geological activity or strengthening a weak magnetic field. A stronger magnetic field, in turn, could provide better protection against cosmic radiation and help retain an atmosphere, crucial factors for maintaining or supporting life. The effect on a planet's core could be even more dramatic. Planets with cooled, solidified cores often lose their geologic activity and, along with it, any magnetic field generated by a dynamo effect. If the energy from a magnetar were to penetrate deeply enough, it might reheat parts of the core, creating localized pockets of molten material. This could, in theory, restart some level of tectonic activity, which is essential for processes like carbon cycling and the renewal of surface materials. For planets that have become geologically dead, this kind of kickstart could have profound implications. The ionizing radiation from a magnetar might also interact with frozen or trapped chemical compounds on a planet's surface or in its subsurface layers. In icy worlds, for instance, this radiation could break down water ice, releasing oxygen and hydrogen. If hydrocarbons or other organic molecules are present, the energy from the magnetar might trigger complex chemical reactions, leading to the formation of more advanced organic compounds. Such processes have been proposed as potential mechanisms for the early development of life on Earth, driven by our Sun's less intense but more persistent radiation. A magnetar, while much more intense and sporadic, could catalyze similar chemical reactions on a planetary scale, albeit in a more chaotic and unpredictable manner. Another avenue to consider is the role of Magnetar outbursts in planetary surface temperatures. While the radiation from a magnetar is overwhelmingly powerful and could easily sterilize the surface of a planet, there are scenarios where this energy could temporarily raise temperatures on frozen worlds, melting surface ice and exposing subsurface oceans. This kind of temporary warming might allow liquid water to exist, even if only briefly. If microbial life existed beneath the ice, it might seize this opportunity to metabolize and replicate, creating bursts of biological activity. On planets where life has not yet arisen, the thawing could mix previously isolated chemical compounds, increasing the chances for prebiotic chemistry to take place. When high-energy particles emitted by a magnetar collide with a planetary surface, they can deposit vast amounts of energy. This energy transfer might vaporize part of the surface, but it could also create a shock wave that compresses and heats deeper layers of the planet. For rocky planets, this could lead to localized melting, potentially reshaping the landscape and creating environments that are chemically or geologically more complex. For gas giants or ice giants, the interaction between magnetar particles and their atmospheres could create dramatic auroras or even alter the atmospheric composition over time. Not all planets would benefit from a magnetar's influence, of course. Those already struggling to hold onto an atmosphere or with fragile ecosystems might find their development derailed by the intensity of such an event. But for lifeless, dormant worlds, especially those far from their parent stars, the energy delivered by a magnetar could act as a kind of cosmic defibrillator, jolting the planet into a new phase of evolution. The long-term effects would depend on many factors, including the planet's size, composition, and distance from the magnetar. Life on Earth, after all, has been influenced by catastrophic events like asteroid impacts and supernovae. Could magnetar outbursts represent another form of cosmic intervention, one that operates on a vastly different scale? While direct evidence of magnetars reshaping or igniting planetary systems remains speculative, studying these possibilities can deepen our understanding of the interplay between stars and planets and the conditions that make life possible. Observing the impact of a magnetar on a nearby planetary system would require an almost perfect alignment of circumstances. A magnetar close enough to influence a planet, but not so close that it obliterates it. Advances in telescopes and space observatories might one day allow us to detect such interactions, offering a glimpse into these powerful processes at work. The future of magnetar research. Upcoming missions and tools. One of the most anticipated developments in the field is the deployment of more advanced space-based X-ray telescopes. Instruments like NASA's proposed Lynx X-ray Observatory aim to offer unprecedented sensitivity and resolution, capable of detecting the faintest X-ray emissions from magnetars, both within and beyond our galaxy. This level of sensitivity is crucial for studying quiescent magnetars, those that are not actively flaring, and for identifying distant candidates that emit X-rays too weak for current instruments to detect. LINX, with its planned ability to resolve fine details in X-ray sources, will allow scientists to examine the subtle variations in magnetar emissions, shedding light on the processes occurring in their magnetic fields and crusts. Another mission that holds promise for magnetar research is the European Space Agency's Athena, or Advanced Telescope for High-Energy Astrophysics. Scheduled for launch in the late 2030s, Athena is designed to study high-energy phenomena with exceptional clarity. One of its key features is the X-ray Integral Field Unit, which will provide high-resolution spectra and imaging. This capability will help astronomers analyze the energy distribution of magnetar flares and better understand the physics driving these outbursts. Athena's ability to survey large areas of the sky could also lead to the discovery of previously unknown magnetars in nearby galaxies, providing new data points for researchers to study. The Chinese space program has also been investing in advanced X-ray astronomy. The Einstein probe, set to launch in the near future, is designed to monitor the sky for transient events like magnetar flares. This mission's wide-field X-ray telescope will be particularly useful for detecting short-lived, high-energy bursts, offering a better chance of capturing the initial stages of a magnetar flare. By observing these early moments, scientists can gain insights into the trigger mechanisms of Magnetar Outbursts and the dynamics of magnetic reconnection. On the radio astronomy front, the Square Kilometre Array, or SKA, is poised to revolutionize the study of magnetars, especially their connection to FRBs. This massive array of radio antennas, currently under construction in South Africa and Australia, will have unparalleled sensitivity to faint and distant radio signals. The SKA's ability to monitor large portions of the sky in real time will make it an invaluable tool for detecting FRBs linked to magnetars. Moreover, its high precision in timing and localization will allow astronomers to trace these bursts back to their sources, potentially identifying magnetars in other galaxies. Ground-based optical and infrared observatories are also playing an increasingly important role in magnetar research. The Vera C. Rubin Observatory, with its wide-field survey capabilities, will enable the identification of transient optical events associated with magnetar activity, such as the ionization of surrounding gas clouds. By pairing these observations with data from X-ray and radio telescopes, researchers can build a more complete picture of how magnetars interact with their environments. Additionally, the James Webb Space Telescope has the potential to detect infrared signatures of magnetars embedded in dense star-forming regions, where visible light is often obscured by dust. Instruments like LIGO, Virgo, and the upcoming Cosmic Explorer are pushing the boundaries of sensitivity to detect subtle gravitational waves. Magnetar-related phenomena, such as starquakes or binary neutron star mergers involving a magnetar, could generate detectable gravitational waves. These signals, if captured, would provide an entirely new perspective on the physics of these objects. The proposed laser interferometer space antenna, designed to detect low-frequency gravitational waves, could complement this effort by exploring different aspects of magnetar-related activity. Another exciting frontier in magnetar research involves high-energy gamma-ray observatories. Missions like the proposed AMIGO, All-Sky Medium Energy Gamma Ray Observatory, are being designed to capture gamma-ray emissions across a broad energy range. Such instruments will be crucial for studying the most energetic flares from magnetars, as well as exploring their potential connection to gamma-ray bursts. By providing a detailed look at the gamma-ray spectrum, AMIGO could help unravel the mechanisms driving the extreme energy outputs of these events. Collaboration between observatories and instruments across different wavelengths is becoming increasingly important for magnetar research. Multi-messenger astronomy, which combines electromagnetic, gravitational wave, and particle data, is providing a holistic view of these objects. When a magnetar flare is detected in one part of the spectrum, other observatories can quickly focus on the same region to capture complementary data. This coordinated effort maximizes the scientific return from each event and allows researchers to probe multiple facets of magnetar behavior simultaneously. Magnetars and the limits of relativity. These stars, with their intense gravitational fields and mind-bogglingly strong magnetic environments, offer some of the most extreme conditions in the universe where the predictions of relativity can be scrutinized. General relativity, Einstein's theory describing how gravity works as a curvature of spacetime, has been tested in many ways. Black holes, for example, are some of its best-known test cases. However, magnetars provide a complementary avenue for exploring relativistic effects because of their unique magnetic fields and dense matter. The gravitational pull near a magnetar, while not as overwhelming as that of a black hole, is still incredibly strong. A magnetar's core, containing about 1.5 times the mass of the Sun, compressed into a sphere just 20 kilometers wide, generates gravity so intense that it warps spacetime in its vicinity. This warping has measurable effects. Light escaping from a magnetar's surface experiences gravitational redshift where its wavelength stretches due to the star's gravity. This is a direct test of general relativity. X-ray and gamma-ray signals from magnetars are analyzed for these shifts, providing astronomers with data to confirm or refine our understanding of how gravity operates in such extreme settings. Magnetars possess the strongest magnetic fields known in the universe, and they create conditions where quantum electrodynamics, or QED, the theory describing how light and matter interact, intersects with relativity. In these fields, vacuum birefringence, a phenomenon predicted by QED, can occur. Space around the magnetar acts like a prism for light, splitting and polarizing it in response to the magnetic field. In the presence of such extreme magnetic fields, electrons and other charged particles spiral tightly around magnetic field lines, releasing synchrotron radiation. The energy levels involved test the relativistic limits of particle motion because the speeds approach the speed of light. This is where special relativity comes into play, as the theory precisely predicts how these particles behave. When a magnetar is born or during periods of intense activity, their rapid spin can create effects predicted by general relativity, such as frame dragging. This phenomenon, also known as the lens-Thirring effect, occurs when the rotating mass of the magnetar drags spacetime around with it. Observing and measuring this effect in magnetars could provide further confirmation of relativity or highlight conditions where its predictions might break down. Magnetars also offer insights into the fundamental nature of spacetime itself. Some theories propose that spacetime might not be perfectly smooth, but instead has a granular or quantized structure at the smallest scales. Magnetars, with their extreme fields and densities, could amplify any such effects, making them observable. And with that, today's journey comes to an end. What other wild space objects would you like to hear about? Send us your ideas in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.